with ICTP Trieste, and is hosted by the Institute of Theoretical Physics, which owns this building. So you are the Institute of Theoretical Physics, and which hosts the ICTP South American Institute for Fundamental Research. So basically, we have several activities related to workshops and schools, and also many outreach activities. We have several partners. One of the most important partners, of course, Perimeter. We have Luis and Jesse here from Perimeter Institute. And the funding comes from mostly from the State of São Paulo funding agency, and also from UNESP, and also from Simons Foundation and other sources. Okay, so this workshop is a satellite workshop of the Cosmos conference that many of you have attended in Rio. It was built around the ICTP-SAIFR prize in classical gravity and applications. So this prize will be given on Tuesday afternoon. So please, you probably know, you saw this in the program. And also announcements, we have a group picture Tuesday just before the end of the morning session, just before lunch. And also there will be a workshop dinner on Tuesday evening. We have more details later. So without further ado, on behalf of the organizing committee, I just want to wish you all a very productive workshop. And I would share the first speaker, which is Professor Valerio Marra from the State University of Espírito Santo in Brazil. And he's going to talk about lambda Lemaitre Thomson-Bondi N-body simulations. So Valerio, please.
Thank you, Rogerio. And well, first I'd like to thank the organizers. This is one of my favorite places in Brazil. It's really great to be here. Okay, so I'll talk about something that perhaps you're not very familiar with. So we'll try to motivate the reasoning behind this project and why it is interesting to carry it out. So this is my brief outline. So I'll go very quickly through the standard model cosmology and tensions, for then focusing on homogeneous cosmologies. So, maybe I have another. So the standard model of cosmology is built upon some. Sorry. I need to press this, right? Okay. So, right. Okay. So standard model of cosmology is built up upon, at least at the moment, if you want, three main observables. And here they are, the CMB, supernovae, and BAO, which is just here summed up with the CMB. So you got in this famous plot the density of matter, the amount of matter in the universe. On the y-axis, the equation of state of dark energy, these unknown components that is accelerating the expansion of the universe. And all these three constraints, they all cross at a single spot, which is consistent with the standard model cosmology, which is the lambda CDM model, with about 30% of matter, 70% of dark energy, and again, the equation of state close to -1, the one of the cosmological constant. On the right, you see the same kind of constraints, but just allowing for a time variation of the equation of state. And again, you see that, albeit with some big error bars, they all cross at the point of the regard that reflects the cosmological constant. So this is I stole this plot from this slide from Rocky Kolb. This is this very summary of our knowledge till now. So 95% is dark, and then you got a little gas, stars, neutrinos, and metals are really rare. So we are quite ignorant about the 95% of the content of the universe. So our main goals, for summarizing very fast, we'd like to know the background evolution of the universe, question 1, and how perturbations grow, question 2. Okay? So at the moment we know pretty well, well, we've seen that there are still big error bars on the evolution of the equation of state dark energy, but we're kind of confident about the background evolution. Perturbations, we are waiting for big experiments like the LSST, Euclid, JPS, and so on. So summarizing, concordance model has very good pros. It's a very good fit to a lot of data, simple and consistent. People are working out the phenomenology, including baryons, and so on. Problems, of course, are the dark matter and dark energy. And recently, there is some bad fit to some data, the so-called tension. So I'm just briefly going through the tensions now. For a comprehensive review, I point you to this nice work by Leandros and Scara. So you got, and this is not comprehensive. You find basically all tensions and anomalies in this review. Here I'm highlighting just a few, like perhaps the most well-known. So you got CMB anomalies. There is the cold spot. So it's a region that is very cold. And it's a fluctuation that CMB anomalies typically are around the 2-3 sigma level. Cold spot perhaps is one of the most prominent ones. And people have tried to look at it from any point of view. Could be a perturbation at the CMB time. Could be an anomalous structure on the line of sight from us to the CMB. Or could be just a statistical fluctuation. And if you do carefully, the statistics, it's all fine. Then you got this lensing amplitude tension correlated with the curvature. And here, there have been a few papers following this issue. So basically, if you allow for this lensing amplitude to be a free parameter, data tells you that its value is some 2-3 sigma ways from the value that should have in the standard model. And then perhaps the oldest and most interesting, at least for me, the hemispherical asymmetry. So if you look at the CMB with the dipole, including in the modeling some dipole modulation, you find a signature for this or dipole or hemispherical asymmetry. One part of the sky is different from the other. And I find this very interesting because it could signal a small, right, but significant deviation from just large-scale isotropy and homogeneity. Then you got this large-scale dipole anisotropies. This has been discussed quite a lot during the last 2 years, especially given the papers by Sekrest and collaborators, including Subi Sarkar. So this is a very, I think it's called Baldwin and Ellis test. It was cooked up in the 70s, 80s, back when there were not really observations in cosmology. And so the idea is that if the metric is really FRW, if homogeneity and isotropy are true in the universe, then there should be a common reference frame in the universe, right? So that should coincide with our motion with respect to the CMB. So our motion with the CMB should allow us to take out our peculiar velocity and find this reference frame. And if you look at dipoles other than in the CMB, say in matter, at redshift, say 2, 3, so at distances which are much closer to us than the CMB last scattered surface, then we should find that by subtracting all these dipoles, we find the same reference frame, because the FRW metric is just 1. So what they found is that instead is a different signal that is in disagreement with the dipole from the CMB at the level of 5 sigma. Okay? So this is a potentially very high significance tension. And to my understanding, nobody's really working on modeling this yet, because it's not easy to model. They call this so-called a tilted universe, so a universe that features very large-scale flows. And so at the moment, people are, I think, focusing mostly on data. And I'm still waiting for some independent analysis of the data, which is all public and available in GitHub, to see which issues there are with this analysis, because 5 sigma is Then changing completely topic, this small-scale CDM problems. So used to be the missing satellites, but now they're finding a lot of satellites with the better measurements. And now it's more the too big to fail problem. So it's basically due to how much baryons and dark matter and how many baryonic activity you expect in a given halo. So there's been mismatch, but this could be a poor understanding of baryons, or well, could be a problem of cold dark matter. Perhaps dark matter is not that simple idea that we have of it. Then, more on the cosmological side, we have the high versus low redshift tension on the sigma 8 omega matter plane. And this has been highlighted by different observables, so by cluster counts, by weak lensing, and perhaps Jesse will talk a little bit about this later. And of course, this is not a severe tension at all. It's like 2 sigma level. Well, it depends on what observer you look at. But surely will be what everybody is waiting for when new data will come, right? Because this is really represents a mismatch between what you expect from the CMB fluctuations and what you observe at late times. And the same actually happens with the tension on H naught. Again, it's the mismatch between what you expect to measure given CMB and what you measure at low redshift. And this, nowadays, I think it is the tension in the standard model and reached 5 sigma last December. Okay? However, I think this is really important, especially for CMB anomalies, because CMB, you got a lot of data points. So you can find anomalies for sure, by definition. So bear in mind that the look-elsewhere effect, which means it's difficult to assess these anomalies because nobody published in the journal of failed tests, right? So you keep looking, you find nothing, you publish nothing. However, the journals we published there are journals of outliers. So basically, all the anomalies, they suffer from significance inflation. This is for sure. How significant is significant inflation has to be assessed. In particle physics, there is a well-known procedure for doing that because you got your accelerator in front of you. Cosmology is more difficult. Okay, so this talk is about inhomogeneous cosmologies. First, what are inhomogeneous cosmologies? So it is the study of the universe without assuming a priori an FRW metric, that is homogeneity and isotropy on large scales. And well, these are three basic motivations. First is to test basic assumptions given our ignorance. Second is just a program to reconstruct a metric from observations. So this is it is possible. Of course, you cannot be totally free. You need to introduce a modeling and constrain your modeling. But it is possible to constrain to some degrees, some metric degrees of freedom directly from observation rather than a priori constrain them. Lastly, and recently, we have these tensions, especially for this field. This knot tension is potentially interesting. However, it showed that inhomogeneous cosmology cannot solve this knot tension. This is a spoiler. And then even more for me, cosmic dipoles and anisotropy. Okay. So inhomogeneous cosmology is too difficult a topic given like that. Okay, how can you do cosmology without defining a background metric? So then one can introduce a subset of it, which I call the early FRW cosmology. So it's a arbitrary inhomogeneous cosmology. Well, the first assumption, is to say that, of course, we want to be Copernican, right? Because we cannot admit that we are really special in such a big universe. So the basic idea is that the Copernican principle is valid on a grander scale. Not just the standard 100 megaparsec, maybe it's a gigaparsec, 10 gigaparsec, whatever, but will be valid at some point on larger scales. Second, these early FRW cosmologies are cosmology which features, so imagine lambda CDM. You put on top some, you put on top some extra stuff. the requirement is that this extra stuff goes away at early times. Okay? So they're all basically decaying modes. Sorry, growing modes towards present time. So you can think of it as a kind of very weird primordial Gaussianity with correlated phases and stuff. Okay? And so this requirements is also something practical, because if you do so, then you can use existing codes, such as gadget or GR codes like Ramsey's concept, etc. Without this subset of cosmology, you're really lost. You can know how, and don't know how to simulate the universe. Especially don't know how to include then the CMB in your likelihood, which is essential to do present cosmology. Okay? So this is the first slide, and I'll come back to this point. But so this is the first line of a series of possibilities for modeling the homogeneous universe. The subject of this talk will be regarding this modeling, which is the step 1. So here we are us, the ICTP, and the space-time is modeled as a Lemaître-Bondi metric, which is spherically homogeneous and isotropic, so it's just a ball, which is embedded into FRW. So at this circle, you go back to FRW exactly. Okay, so it's a large-scale perturbation spherically symmetric. Justification is this one. It's so-called spherical cow. It was, I think, invented back in the States half a century ago. So it's the way physics work. We want to simplify as much as possible. So this is the first step. So I'm not saying this is a good approximation. It's the first step. So and this is then what I call the lambda LTB model, which is lambda CDM endowed with a spherical under or over density. Okay? Second approximation, and this is worse. Where is the observer? At the center. Okay? So these are two separate things. How you model space-time, where you place the observer. So at the center, justification. Well, if this structure is nonlinear, it's a good approximation. Because a posteriori, we know that CMB constrains the observer at the dead center of the structure. Otherwise, there would be a huge dipole in the CMB, and this cannot be, right? So if nonlinear, this is good. If, however, the structure turns out to be linear, then the approximation is not so good. Basically, you're saying that you're averaging observation over angles. You're neglecting anisotropic degrees of freedom. And at the end of the day, what happens is that anisotropies are as important and radial in homogeneity, so the modeling is not as satisfactory. So this next step would be indeed to move the observer from the center. But for this talk, the observer will be at the center. Again, due to manpower limitations. So what is LTB? A quick slide to summarize it. So here, using a trick. So I'm hiding everything under the carpet, all the dust. Why? So this looks very much like FRW because the way it is written, but it's more complex, of course. So you see, it's just FRW, but things get subscripts and R dependencies. So in FRW, you got these two scale factors are the same. The curvature is a constant. Here is a function. Because of these two different scale factors, you have two different Hubble scales, Hubble rates. And this means that you distort, for example, BAO in different ways, along the line of sight or perpendicular to it. The Friedman equation becomes something like that. Again, I'm hiding everything in a smart way. So this is it's not really the matter density. This is the integrated matter up to that shell, excluding using a Euclidean volume integral anyway. But I mean, this is when you go to LTB, you generalize your matter in this way. Cosmological constant remains the same, and then the curvature gets an R dependence. You can also write it as a function of R-dependent density parameters. So this metric is defined by a set of functions. Some are gauge, so they are not interesting. The physical ones are curvature, which give you growing modes. Okay, so you perturb the curvature, you have a growing mode in your solution. And then you got the bank time. So you can decide when the universe started. Okay? And this gives you decay modes. So as I said before, I want to only study early FRW cosmology. So in this case, you need to kill the decay modes. So you put a homogeneous bank time. Okay? So the only free parameter here is the curvature function, which we model in this way. This is a way to match the metric at a finite radius. And the only free parameters here are the background curvature, which we're going to use flat most of the analysis, and the curvature at the center, which defines if there is a center over density or under density. So here to give you an example, I'm done with time. So we got here the radial coordinate. So this is, imagine this as an FRW coordinate, like a simulation box coordinate, and not a gauge coordinate. So this is just your box, and this is your density profile, and this is the integrated profile. So in order to have a matching at a finite radius, you need to compensate the underdensity with the overdense shell, and vice versa. And so you see the kind of fluctuation, the density parameters. The density parameter is lower here, you got curvature, etc. And here I'm showing the Hubble rate. So you see that locally you have a higher Hubble rate than globally. Okay? And then when you have when you have this big it's weird.
Where's the mic?
I don't know.
That's the problem.
Okay, well,
let's see if it's better now.
Okay, better? Okay. So you see, an interesting point that will be relevant for for later is this departure here. You see, when you've got spatial gradients, so in a homogeneous metric, it's characterized by what? By spatial gradients, because if it's homogeneous, you go back to FRW. So when you have the spatial gradients, you have a big difference between the two Hubble rates. Okay? So this is a trademark for inhomogeneous cosmologies.
I have a real question now. What's the difference between the small delta and the capital delta?
So delta is the local density contrast.
People ask without the microphone, please repeat the question. No, you can repeat the question.
Yes. Okay. So Rogerio was asking what is the difference between small delta and big delta. So small delta is the local density contrast. Big delta is the integrated density contrast. So take into account all the matter from the origin to a given shell. So this is why it never, you see, what matters for the matching, for the Israel boundary condition is the integrated contrast. And it has to reach exactly the FRW value to have the matching. Okay? So again, you have a compensating shell if you have, no, compensating overdensity if you have an inner underdensity.
So the matching is at 2000?
Exactly. At 2000, you are in FRW locally.
Both go to?
Yes, both go, but by construction. But you know, here you're at FRW value. But there you're not in FRW. Okay? So naively, you say, you got a solution for the Hubble tension, right? Look at here, this is 73, right? So in principle, you can easily, you put some whatever structure, and you fix the Hubble tension.
Valerio, just one more question, sorry. You do have a physical overdensity in your 2000, the blue one? Is it physical?
Yes, exactly, it's physical. So you have, so again, the other question was if this is a physical overdensity, and it is yes. You got, so the idea you have an underdensity, and then a higher density shell, and then FRW. Vice versa, I'll show another plot later, you can have an overdensity, then a surrounding void, and then FRW. Okay. Here I'm giving the equations for the Newtonian potential, which is given as a function of these curvature functions. And these are how the luminosity distance and Hubble rate change on the light cone. Okay? But again, let's look at this Hubble tension thing. sorry, no, first I need to discuss the Copernican prior. So, okay, you're free to include this in homogeneity, right? But is it allowed by standard cosmology? To do that, we need to build a statistical measure for that. And the idea is to let observations constrain this arbitrary homogeneous metric, that is the parameter RB and ZB, which would be the size and Kc or delta Z, which would be and the contrast of the homogeneity, that is how big and deep it is. So observation will constrain that. Our expectation will be given by the standard power spectrum as constrained by the CMB. Why? Because if the universe is FRW, right, this fluctuation at CMB time should also be here. So the same physics, same fluctuation should be present at these different places in the universe, because the universe is homogeneous and isotropic. So this Copernican prior is built in the following way. So sigma is just the root mean square fluctuations on a given scale, just the mass fluctuations. Delta is instead the size of the inhomogeneity, right? So this prior depends on, again, those parameters that I told you before, the size of the structure and its contrast. And this tells you how many sigma away you are, given that scale and depth from standard cosmology, given the parameters from the CMB, which are convolved via their likelihood. Okay? So this prior simply tells you, no, if standard cosmology is true, that this is the distribution of possible contrast and sizes. Okay? Observables, we use CMB, latest, the Pantheon, not the Pantheon Plus. Pantheon Plus is more recent. Then we split supernova between old data and just a low redshift sample that is used to fit H0. Cosmic chronometers, BAO, comet-wise distortion, kinetic noise Zeldovich, and also local calibration for the luminosity absolute magneton from shoes. Okay, so basically all data that we have, except perturbation data. So regarding the local calibration, just very quickly, so determination of H0 by shoes is a two-step process. First, you need to build your ladders to constrain the luminosity of the supernova. Second, you use Hubble flow supernovae to constrain H0. Okay? You want to do that model independently, so people have been using cosmography to do so. And with the detail that shoes collaboration adopts a cosmography with fixed values of the acceleration parameter and jerk parameters, which are justified because these are the values that correspond to standard cosmology. So it's a bit circular. So this means that the determination of H0 by the shoes collaboration does assume higher redshift measurement. Okay? So it's not really model independent. So we proposed that one actually should skip this second step altogether. No, you don't need to do that. Why? Because you can just do your cosmological inference with your favorite model by including a prior on the absolute magnitude of supernovae. In this way, you avoid double counting supernovae, you avoid using cosmography, even worse with the fixed values for its parameters. And also include further information analysis, the values of the calibration, because you're not free to, people have been doing cosmological inference in kind of a bipolar way, because you use H0, and H0 demands for calibration of the absolute magnitude of supernovae. Then you use supernovae with CMB, and you let MB with the flat prior. No, ignorance prior, but you're not ignorant. You do know the value of MB. And then CMB would push MB towards a value which is different from the one that is required for the H0 measurement. And this inconsistency usually is not accounted for in analysis. But if you do include a prior MB, this is correctly taken into account. And we show this, how this works with the hockey stick dark energy. If you're interested, you can look at this paper. And we also, basic idea is just you don't put this chi-square in your analysis, you put this chi-square in your analysis. Just that, very simple. Okay? Anyway, nowadays also SCHUS collaboration acknowledges that, and they released for the first time the likelihood for the calibrations of the supernovae on the cosmic ladder supernovae. So you can download their Cosmosis code and include just the calibration on the supernovae, and then analyze it with your favorite cosmology. It could be F of R, DGP, interacting dark energy, you name it. Okay, well, it's just a parenthesis. Anyway, so going back to the main question. Can a local void solve this tension? First, can the standard cosmology solve this question? So in standard cosmology, you do have local voids. No, they are allowed. It's not that it's forbidden. However, this is called cosmic variance, and is given by just standard fluctuations. And turns out that it gives at most 1 kilometer per cycle per megaparsec, very generously at most. But you need 6. So no, this is not n. So standard cosmology cannot do that. What about an arbitrary inhomogeneity, right? The one beyond. So you need some mechanisms to produce these anomalously large underdensities. So if you include CMB, full spectrum, right? The supernovae that Rees and SCHUS use to constrain H0 in this range, and then the calibration on MB from Cepheid, then yes, you can. Local H0 is compatible with CMB, with everything. The value is great. And then homogeneity that you need is far from what you expect from the standard model. So this is the Copernican prior, what you expect from standard cosmology. However, as soon as you add all supernovae, you go from red to black. So, and you go from this blue curve, sorry for the color that I inverted, from the blue to red. So basically, if you add all supernovae, you cannot anymore explain the Hubble tension. Data do not allow for a large underdensity nearby. As simple as that. Okay? The measurement of the luminosity distance are very accurate. So this is not a solution. Okay? This plot instead shows, focuses more on the constraints on the space-time, given all available observations, the one that I listed before. So again, CMB, supernovae, BAO, kinetic, Y distortion. And at the end of the day, you reach constraints that are given by these black contours, which are very similar to the one that you expect from a standard cosmology, okay, from the Copernican principle. So you could say that, all right, we confirm the Copernican principle, we confirm FRW, and so on. You also try to reconstruct the metric by allowing for a more general density profile. And the metric does exhibit a local underdensity, but it's too small to explain away the Hubble tension. And it's 2 sigma compatible with standard cosmology. So this is, if you want, the local reconstruction of our space-time. So you could use these results if you want to account for, to decrease the effect of cosmic variance on the position of the observer. Okay? However, there are, of course, this analysis just a first step, because the constraints are tight, but the setup is very simple, very simplified. It's not just the observer which is at the center, who is the center, but also the profile which is rigid, monotonic. For technical issues, you cannot do better than that. Okay? Second, constraints here comes only from background observables. But the real name of the game of the future is perturbation observables, growth of structures, LSST, Euclid, JPAS, you name it. So if you really want to make progress with the more general modeling, so you need more information, you need to account for the growth of structures. And this is why I started this BHOMO project, Cosmology Beyond Homogeneity and Isotropy. So the idea is to study numerically inhomogeneous cosmology. Okay? So it is not possible well, you can write down the equations for the growth of perturbation in homogeneous background. It's very complicated. It's almost, people have tried to solve it numerically, but I didn't see a clear answer to how one can use that modeling for comparing with the observations. Okay? And however, one can tackle this problem with numerical simulations. Okay? The next steps, of course, would be a better modeling of homogeneity. But for the beginning, we started with, again, the lambda LTB model, the simplest possible ЛЛTB cosmology, which, again, is a kind of an archetype of homogeneity in order to explore the effect of spatial gradients on the growth of perturbations. If you want to see more information, you can find them at this website. There's the big QR code there. So why can you actually do numerical cosmology? It's not trivial. So the lucky bit, at least for lambda LTB models, is that Newtonian codes can reproduce the evolution of a general relativistic metric such as LTB, even at larger scales. The reason is basically because of spherical symmetry, and because it's the matter component are just dust and cosmological constant. So you do not have neither sound waves or gravitational waves. So, and thanks to this is a scale invariant evolution, which can be described via Newtonian codes. Okay. So this is a for more general model. This is not certain. One has to check this again. How accurate are Newtonian codes, such as gadget, to model in homogeneous cosmologies? Growth of perturbations. So because of mode coupling, basically you can think of this as a standard perturbation becomes second order, because you have a background in homogeneous background, which is your first order perturbation. On top of it, standard perturbation, which becomes second order. Then you have mode coupling. So it becomes a big mess, such that even linear perturbations, you don't really know how do they grow. So really, this is a unknown territory. And again, the goal of this BHOMO project is to understand and model this via the method of numerical cosmology. So at the moment, I've run a suite of 68 simulations. Every line is actually 13 simulations, more or less. Various boxes of different sizes. And for each box, you have various contrasts. All this data is available. Of course, the snapshots are not, you cannot just download them because being large, the transfer cannot be made available. But if you're interested, please contact me. And because I need manpower to analyze the snapshots, and you can do a lot of interesting physics with this. Okay, so please contact me. Cosmology is fixed to some, I remember, Planck plus DES cosmology, some concordance cosmology. And what is changing are only the inhomogeneous parameters. Okay? For each box, you also have a lambda CDM simulation to compare things. So here I'm showing how the background evolution is recovered within the simulation. So these are simulations that are run with no perturbations. So AS basically 0. And you see how the Newtonian simulation correctly describes the evolution, very nonlinear evolution, up to, given the scales, for any scale, any box. Okay? All right, initial conditions. Initial conditions, there should be a GIF. So initial conditions are given in this way. So you just add to the standard potential given by your Gaussian perturbation, a standard potential given by your inhomogeneous perturbation. Okay? And then you feed these, so you use this Falcon IC code. Then the special initial conditions are just fed to a standard gadget. No, we use Open Gadget 3, but you can use any Gadget 4, any variations. Okay? Interestingly, we use the same lambda CDM seed. So you this is nice because you maintain the large-scale structure. So you will see that in homogeneity, we'll deform filaments and voids, right? Because we kept the same seed. This is really, so here you see the subtle change between one simulation and the other. Of course, all these plots are for exaggerated parameters in order to maximize the visual effect. So here, okay, the resolution is good enough, I think. So here, these are 3 simulations from one of the smallest box 1, the smallest. So this is lambda CDM. This is central contrast, central over under density. So you see, for example, this filament here is present in all of them. It gets distorted because of the background evolution, but also structures grow differently. You see that there is more structure here than here. Okay? So we want to model that, because background evolution, we know it. But we like to really know how perturbations evolve at these different positions. So this is the same plot, but no, just checking the radial profile, if it agrees with the solution from GR. It's all good. This is the same stuff, but for a box 3, much larger box. So you can see the inhomogeneity better because you average more over smaller structures. At larger scale, everything gets more homogeneous. And these circles, they mark, this marks the matching to FRW. So everything beyond this point will be exactly the same. So this arrow is the same as this arrow and this one. Inside, instead, it will be the evolution. And this smaller circle marks the transition between underdensity and overdensity. Okay? And here, because it's a much larger box, you average cosmic variance over, and you agree very well with the GR solution. Here is a GIF. If it's working, yeah, it is. This is just going through the different simulation, changing delta Z, delta naught. Okay? You see, this is particularly interesting to see how the structure are maintained but weakened, because of the structure. You see how the distortion in the cosmic web. All right, so data products. So we got full snapshots for 12 snapshots, totally available. Only the even one are kept, but all the other ones were all used to produce halo catalogs from Rockstar. We got 40 properties, so fully characterizing the halos. And lens planes uses slicers. And this is interesting because of the matching condition and boundary conditions, you can be light cone as you want. You can glue things, doing like a mosaic. Right? So you got a lambda CDM light cone, a light cone with a lot of structure in between, but you can also put just one structure anywhere you want. So for example, if you'd like to study, to have a model for the cold spot given by an intervening a structure that is in between us and the CMB, this would be like a very good modeling. Okay, so now let's go to the modeling. So the background level, LTB is silent. This is a name that was given by Matarese, Bruni, and collaborators some time ago. However, at the perturbation level, we got that the magnetic wave tensor couples to scalar to tensor perturbation modes. And this is a big mess, becomes a nightmare. They've been grouped by Chris Clarkson, Bartelman, and also another one in Japan. They were trying to tackle this, but with no, I think, concluding results. So you got these 4 possibilities, full set of couple equations, a nightmare, silent approximation, I will describe it now, local FRW approximation, or second order perturbation theory.
Question before you go on. So as you said, when you have a transition, you have to satisfy these junction conditions. But that means there is a shell there with specific properties. So you have a fluid with some particular properties. Is that fluid sensible and should be there in nature?
No, it's just dust and cosmological constant.
Can you repeat the question?
So, okay. So Luis was asking if given to the matching condition, you need to have some weird fluid to allow for that. Sometimes you can have discontinuities, this kind of stuff. But no, it's the matter content is just dust, conjugate constant, and just you modulate the density profile such that at a finite radius, you reach the values, the background values. And at that point,
But I'm talking about the fluid on the shell as the transition takes place. So there is a discontinuity across that transition. So what are the properties of the fluid there?
on the shell, the transition on the shell in between LTB and FRW. Okay, right. So we use continuity is up to. So we use 3 times differentiable. So actually, it's continuous down to. No, we have continuity at all relevant orders. So there's nothing really going on. I mean, it's a smooth transition between an LTB to FRW. Yeah. But we can discuss later. Okay. So here I'm talking about the silent perturbation approach and the local FRW. So this was basically this is work by Zibin, 2008. He laid down all these equations. So you do a 1 + 1 + 2 decomposition, exploiting the symmetries of the LTB matrix, spherically symmetric. So you can write this. You can write these 4 scalars. So this is the local density, local expansion, shear, and this will be the electric wheel scalar. Okay. And then you can look at, so at the background level, it's all fine. Right? There is an analytic solution. Not really an analytic solution. If there is lambda, we need to do some, well, it's a bit more complicated, but you can have an almost analytical solution. At the linear level, you have this. Right? So you introduce your perturbation variables, and this is a set of equations. You give the initial condition at method-dominated area, etc. So you give initial conditions, you solve these equations, then you can build a set of transfer functions. So here X stands for these 4 scalars. And then you have these things basically transforms the initial values for these quantities into values at a given time, a given R. Okay? So these are LTB transfer functions. So you have the standard transfer function in cosmology that are there, of course. And these are what they transform those initial perturbations, because we assume that thanks to the metric being early FRW, that at early times you can do harmonic decomposition and everything. So you take those perturbations, and this transforms them into their values at the present time. Okay? So it's a very convenient way to model all this problem. Credit to James Zibin. Now, if this element here in the set of equations is negligible, right? Then basically you decouple density and expansion from the other two, especially from the more complicated ones, and you go back to standard cosmology. Okay? It's a standard cosmology, of course, with some specific parameters for this local Hubble rate and density parameter, which are not, these are like effective parameters. They are not realized locally, neither globally. But still, it's an equation that is trivial to solve. And then, it would be very interesting if you could model the growth of perturbation in LTB using such a symbol approach. Of course, this is true only if this term is subdominant. And you could compare it with for example, this term here, and make a ratio and check if this is much less than 1. So if you do that, so these are two examples of inhomogeneities. So this is central underdensity. This is a central overdensity. You see the matching is again at this dashed dotted line. The Hubble rate is higher here. Here is lower than global, etc., etc. But you see that in this case, that is it's a large inhomogeneity, no, minus 0.4 and plus 0.4. This gamma, that should be much less than 1, actually is not much less than 1 in this case. It goes to minus 0.3 for the underdensity. For the overdensity, smaller. Why is that? This is because of intrinsic dynamics of Ltb. And Ltb eventually gives rise to shell crossing because this central underdensity keep pushing. The background is fixed because you got the matching. And what is in between gets squeezed till you reach shell crossing. That is, you have two shells the same point. And for this reason, underdensities they feature more larger spatial gradients than overdensities. So in this plot, the other way around, you look at the dependence of gamma at a fixed radii as a function of delta naught. So actually, you see that this local F double approximation is not expected to hold in general, not at all. However, if deviation from homogeneity are within perhaps 10%, then it could work. But that has to be tested again, because this is just order of magnitude estimate. So clustering. So in FRW is the standard stuff. You have your power spectrum, you put it inside, you put your window function, in our case is constant, and you get your CL. In LTB, within the silent approximation, you need to beat a much more complicated transfer function here. You have the standard transfer function, so you have the LTB transfer function. It's a big mess. But in the local FRW approximation, the difference between LTB and FRW is just an overall factor. Just the power becomes different. Okay, so the modeling, in order to respect the symmetry, you have to model observables accordingly. Well, you can also take different points of view, but at least at the first step, we only look at angular quantities, because it doesn't really make sense to compute a 3D power spectrum if you do not have homogeneity and isotropy. You can do it if you look for a signal. This is another project we have in mind. And we computed CLs using Hill peaks and W is core func. And this is very preliminary. So these are Hill peaks maps from the simulations. And these are the CLs. The modeling is working. Now we are applying to the lambda LTB. Preliminary because, again, we are limited by manpower. So if, again, someone is interested, please contact me. OK, so we have a list of many papers. So the paper 1 is already out. Paper 2 is a linear modeling. Paper 3, we like to do a path-like cone analysis, then looking on nonlinear perturbation, lensing, Hale abundances, biases. Hale abundances especially can be very interesting because you can look at the effects of secondary bias and stuff. Halo profile concentrations. And then, you can study dipole, bulk motions, and fractal dimensions, and you name it. There are many things you can do. Before concluding the very last minute, just a future perspective, my take on homogeneous cosmology. So I already talked about this. We are here at this moment. Second step is to allow for any size contrast and off-center displacement of the observer. So we would be here. Space-time will be still the same, still the spherical cow. But spherical cow is not too bad, actually, because voids do tend to get spherical, for example. And halos are modeled always as spherical halos. So why not, right? It's not necessarily terrible. So here, we're working on this right now. We need to build an off-center ray tracing module, which is not trivial. And we expect important constraints from the CMB. So CMB actually is the main issues, I think, with having a generally inhomogeneous model, because there is little anisotropy that is allowed for by CMB. Another step could be you take the same LTB, and you just make thanks to the matching condition, you can put as many as you want. They cannot cross, of course. So this is not very precise because you got bubbles that cross in the Swiss cheese, but nevertheless, this is called the Swiss cheese model. You can place the observer as where you want. And this is a smart way to bypass the limitation of LTB. That is a fixed profile and side, then you put many, then you can change profile for every void. And the construction is quite trivial. The integration, the light co-integration, not so perhaps. Then you can go ahead and, okay, let's switch metric. Let's go to Saccharis, the next easy thing. Saccharis still has a matching at a spherical radius, but inside it features a dipole inhomogeneity, right? But again, the LTB is already a pain. Imagine Saccharis is like a long list of free functions. Is it really worth it? Why? So we've seen with LTB already, from the CMB itself, naively we expect, we cannot have big departures. We are looking at percentage effects. So the idea in homogeneous cosmology, I think, is what if there is, at large scales, some percentage effect, some 0.03 contrast structure that could give you interesting signals, hemispherical isotropy, cosmic dipoles, etc. But for that structure, you don't really need a general relativistic solution, right? Because those are useful when you have no linear structures. And of course, being exact, you don't have to worry about convergence. But for nonlinear, but these are ruled out. And so I think that the next step really would be a perturbative approach, trying to find a smart way with not too many degrees of freedom to model the inhomogeneous universe. Of course, you need to test this with simulations, and not just, at the end of the day, you want to run Newtonian simulations because those are cheap to run, very well tested, and can give stuff that you can use to compare with observations. But then you have also to test some lower resolution version with GR codes to make sure that you're not simulating something that doesn't make sense. Okay, because again, you are departing from FRW at gigapart scales, perhaps. So, well, this is the program that I started, and many years to come to reach this level, but that's all. Thank you.
So questions? Yes, many questions. That's great. So first, go here, then I do have time to go there. Sorry.
So thank you for the talk. The LTB metric is spherically symmetric, right?
Yeah.
You have a center.
Yeah.
And isn't this a special point? How do you conciliate this with the Copernican principle?
Yeah, so this is indeed the very problem of this first setup. So there are two separate issues. The modeling of the space-time. So when you model the space-time LTB, the observer is not there yet, so there is not problem for an observer. So no, that's the spherical cow problem. Okay, so you need to think if a 1 gigaparsec structure, spherically symmetric, makes sense or not. Probably it's a very spherical cow problem, so probably it does not really. Second problem is the observer, and you're correct. If you're at the center, it's a gross violation of the Copernican principle. Indeed, these are called non-Copernican principle. It is non-Copernican, were the so-called non-Copernican alternative to dark energy. So back in the day, people were really trying to explain away dark energy with this. The simple idea is that you can alter, you can change your light cone. So faster expansion now than yesterday becomes faster expansion here than there. No, you have total degeneracy. You can reproduce with LTB any luminosity distance function. Totally. Okay. So, but these models were ruled out, right? They produce too much kinetics noisy dodge effect because you have you have insanely large velocities going outwards, and so matter will interact with CMB, and we give you signals that are ruled out by zillions of sigmas. This was a famous paper by Zhang and Stebbins, and later by Zibin also. So we are not trying to, so we're not the center of a void. We are saying of an homogeneous structure of any contrast. So if this structure is nonlinear, yeah, if it's nonlinear, then you really need to be at the center. Because in that case of the center, so you need to be within 20 megaparsec of the center, 50 megaparsec. Otherwise, you would have a too large dipole with respect to the CMB, and then you basically, I mean, you could hope for some cancellation, for peculiar motions, for the peculiar velocity, but this will be only one soldation. But in that case, if it's nonlinear, you're really explicitly violating the Copernican principle. So you're testing the Copernican principle. That is fine. I mean, if you're testing it, you build a model that is non-Copernican to exclude it. Okay? So this is fine. And we did this because I cannot go too much, but when those plots with the contours, you would see that the black contours would match the expectation in green. So you cannot have large structures, a deep structure at a large radii. So this worked, this assumption was okay to be falsified. But now when you want to constrain the local space-time, then you're at a very nonlinear scale, very linear scale, like a few percentage of contrast. And at that point, yeah, it becomes a problem of modeling because you are placing, again, at the center without really a motivation because you don't want to falsify Copernican principle anymore. It is just a lack of modeling. So to solve that, you need to, at that point, really let the observer, the distance has to be a free parameter in your MCMC chain. Right? So at the moment, we have lambda CDM, all the parameters, plus radius and depth. Now we want to also add the distance of the observer from the center. And then you let the data tell you what it is.
Thank you.
So sorry, I go first on this side and then on the other side, so that I don't have to go back and forth.
So a little bit in line with what João said. Since you fix the observer and you're measuring all the quantities at the observer since you're receiving the signals, wouldn't that kind of violate gauge invariance? Because, for instance, in Robertson-Walker, and sometimes when you want to measure some effect from CMB, you change gauges because it's easier to follow the light rays. So how can you link the perturbations in limited on-bound to the perturbations in lambda CDM if you're not, if you don't know exactly what the gauge you're using, and since you already postulated an observer, you can't change gauges because, well, you're already assuming gauge.
So let me see. So at the background level, so all the constraints, so the observer here was at the center only for background observables first, because that's what we can do at the moment. We cannot compare with the gross of structure yet. So for the background, you have this metric. You can read the luminosity distance directly from it. And then the gauge here is given by you are free to define your R coordinate. Mm-hmm. Right? You can change it as you want. And but the luminosity distance, once you define it, is it's a gauge independent. You're observable. You solve the equations, and I mean for all the background observables, you can solve them in this way. So that's fine. For perturbations, then this R coordinate is something that is tricky and has to be taken into account. So you cannot so the equation that I gave you here, and here, no, here there is not an observer yet, right? In this, where is it? Yeah. So here it is this R coordinate, because to solve this equation, you have to you use the metric coordinate. But then when you compare to the to the simulation. Simulation lives in your N-body gauge, right? So at first order, this is the same as this chi coordinate that is defined in a way, but it's the one that matters from the simulation. So you should be careful in using the correct coordinates, and that's no trivial issue, actually. I was working on this in these last months, how to correctly account for this.
Yeah, because I mean, since you're observing from the center of the homogeneity, it seems to me that when you go to the perturbed level, you can't change gauges that easily as you can, for instance, when you assume conformal Newtonian gauge and you already say these are the gauge invariant perturbations, right? How do you define these in LTB?
You can, no, you can, if you can still, when you give initial conditions, where is it? No. Where is it? Here, yeah. So oh, okay, this is a linear level.
Maybe we can discuss that later.
I mean, you should imagine this at the simulation level as just another perturbation on top of what you have. Because in simulation space, it is FRW. It's not LTB, it's FRW. The box evolves like according to FRW, all the particles, blah, blah, blah. Just a perturbation, which luckily, its background evolution follows the GR solution because this GR solution is very constrained, it's very symmetric, dust, etc., scale invariance, all that. But yeah, but that's like kind of a coincidence. You could, so if you look at just as another perturbation, then basically you can apply the same.
Okay, thank you.
Stuff. I don't know if I was clear.
Hi, thank you for the talk. Do you have any talks, or what would be the challenge for LSST data products related to inhomogeneous model, or any thoughts on that, or challenge how to calibrate something?
Yeah. That, of course, with the LSST will be, if you want to explore, because this is really interesting only if you explore large scale, very large scale homogeneity. So you want deep surveys. So LSST is deep, and for sure you can it will be very useful to, once we have a theory, a modeling for the cross structure, it will be very useful to constrain that. Now, all the calibration work tools will be done for lambda CDM. But again, it will be very small departures from lambda CDM. Perhaps smaller than modified gravity models. Perhaps will be more conservative this than, will be, so perhaps you could trust more, enough the data products to be applied to this kind of analysis. But regarding future data, what I'm even more excited than LSST, I'm sorry, but is dark sirens. Because with dark sirens, you go much deeper. So if you manage to use them for cosmology, there really you can constrain super large structures. Because basically you see all the events up to when we first start having coalescences. So that's big. But LSST will be surely, because it's deep. In Euclid, of course, also. There's
So Valerio is a member of LSST. He forgot to mention.
Yeah.
So you can propose a project for this.
So thanks for the nice talk, Valerio. So yeah, actually I had a question that you already answered before, but if I can, it's more out of curiosity. I saw that you mentioned about also anisotropic cosmologies, probably. You actually mentioned Bianchi cosmologies at some point. I just was wondering if you're planning also to explore these kind of things, or
yeah. So that's a common one. Even Planck tested some that weird Bianchi with also with the spin. The thing is that you need to give initial conditions at early times. So at early times they have to become LFRW. And Bianchi, being homogeneous and anisotropic, so I have made that. So I was thinking about how to, if it's really possible. I didn't think very hard actually about that. But if you, because I never played with Bianchi, but if you have if you have played with them, you have some ideas, because it's a very practical issue. You need to have a CMB code to generate initial conditions. So, and that you need a model that satisfies that. Otherwise, you cannot simulate, you cannot do cosmology. Of course, you could imagine, okay, let's build a CMB code for inhomogeneous, who can do that? I mean, you need that's not trivial, right? But it's a good question. I haven't looked at it really. I just just thought about it.
So any more questions from this side before I go to the other side? Okay. I think Jesse has a question, right?
Hey. So in this scenario where you end up having like an overdense or an underdense shell at some distance, it seems like it'd show up in peculiar velocities, and naively, it seems like maybe studying the impact of that on like the apparent linear growth rate might be simpler than modeling the whole power spectrum. Have you looked at how RSD constraints on like F sigma 8 at different redshifts whether that can constrain this?
So, let me think. So, okay, so let's go to one of these pictures. Just to get the, where is it? Here. So, yeah, so you got, for example, under density, then you got the, then you imagine being the light cone, right? So you're the center. So so he, and then you look out, and then yes. So eventually, yes. So once you have a model, again, you need a model for the growth of perturbation to compare with to see how F sigma 8 could change yeah, that's interesting because giving this modulation, you could have a degree of freedom to explain some and other parts and the different redshifts. Yeah, that eventually, yes, we'll do that.
Yeah, and I can mention it maybe in my talk or later, but we looked at this model with like bin sigma and redshift, and one of the things we ran into that we had to figure out how to handle was if you like arbitrarily change the density in different redshift ranges, that'll give you implications for matter flowing from one shell to another.
Ah, interesting. Yeah, and anyway, this profile modeling, again, is people have been trying to work with a more general profile, so you can imagine some nodes of a spline, and then have some freedom in modeling. But again, I wouldn't do that with lambda LTB because lambda LTB, if you get into shell crossing very easily. I think, and it's not worth it because if it's linear, anyway, you can just do some perturbation stuff.
Since you are at this slide, regarding these compensated profiles, it looks like, for me, it's like you have a fine-tuned model because you really need that profile to average at 0 to have Friedman-Robertson-Walker after some scale, right? how difficult would be to implement a profile that you get FRW asymptotically?
Okay, so originally people were doing asymptotically, indeed, because well, it could seem more natural, but then it's dangerous because if you do MCMC with this model which can have arbitrarily large radii asymptotically, you could touch the CMB, right? So when you are the CMB, you want to be FRW exactly. Otherwise, you can introduce biases and issues. So, and actually, it's not really fine-tuning because you see, you should look at it from the curvature function point of view. It's just that the curvature function goes to 0 at some finite radius. So instead of, so got your R, oh, these are big, okay, and well, just put here that is more visible. But instead you can do this, or you can do with a hyperbolic tangent and go into infinity. For many things could be equivalent, right? But so the issue is here that you need to ensure the derivability for the metric function, Christopher symbol, everything to be fine. But this is just a technical issue. But doing this is much safer because, yeah, for many technical things, for example, how you define, essentially the main motivation is to avoid to be in FRW at the CMB time. Let's say redshift larger than 10, to be sure. Because hyperbolic tangent is not, if you let the parameters free, you never know. Yeah. So it's really, once you ask for that, automatically you have a compensated shell.
Yeah.
Because what enters the dynamic is only the capital delta. So it's delta that matches. So it's a side effect that comes in a compensating shell.
Okay, any further questions? I'm not sure if Ricardo Sturani is looking at the YouTube channel to see if there is any online questions. But, so I have a curiosity question. You mentioned Sarkar's and collaborators' work in the beginning, and there are some claims that they have detected some anisotropy or some homogeneity, no? From Sarkar's group.
Yeah. So they looked at quasar.
Yes, and it doesn't agree with the direction of the
Exactly.
dipole.
So they found. Yeah, I don't have a slide here, but so they found that looking at the fluxes. So there is a way to parameterize the effect of a peculiar velocity with respect to the quasars, and they find a phi sigma signal.
But you claim here that there's no. You looked at this and you didn't find anything, right?
Sorry.
You looked at this effect. Not on this particular observable, but other observables, and you didn't find any sign of an isotropy or anything, or maybe I misunderstood?
No, Sarkar and the others.
Yes.
I mean, so they found that the alignment of this quasar dipole is consistent, I think, with the CMB, more or less. But the amplitude is different. That's agreed at phi sigma.
Okay.
And then also they compare it with other anomalies. So you have the quadrupole, octupole, the axis of evil, and they were not much significant. I think that basically the thing is looks like the matter frame and the same frame are different.
Okay.
And with the tilt, with the flow, which is consistent in the direction.
Okay. Can that be fit in an LTB model or?
So you could, yeah. If you have a huge LTB and the CMB is within. So actually, I'm working with on that with some collaborating with Miguel Quartin, and Otário da Vicamarena. We're trying to see what to do there. But yeah, it's not clear yet.
Okay. So Ricardo, no questions from, okay. Okay, so I don't see any hands up. So let's thank again Valerio for this very
Thank you.
So we break for lunch. I think there's some maybe suggestions in the package of lunch. If not, just follow a local person. There's several nearby places, per kilo places. What? Sorry. We start at 2, yes.
they have not sent the one-page PDF to advertise their poster. So do it as soon as possible, because at the end of the afternoon session today, there will be this one-page PDF will be loaded one after the other, and you will have 1 minute to catch people's attention and to induce them to go and look at your poster during the coffee break. So I repeat: João Paulo, Daniela, Nicolas, Felipe, Neil Lisander, Mario Raya, Angie Milena, and Edson Magno. Send your one-page advertisement of your poster now.
Okay, so let's start the afternoon session. It's my great pleasure to introduce Dr. Jesse Muir from the Perimeter Institute of Theoretical Physics in Canada, one of the major partners of our institute here in São Paulo. And Jesse is a member of the best collaboration I know of the Dark Energy Survey. And she's going to talk about testing general relativity with the Dark Energy Survey galaxy clustering and weak lensing. So Jesse, please. I have we have 50 minutes plus 10 minutes for questions. Okay.
Okay. Can everyone hear me? Great. Yeah, so there's a couple of changes from the schedule that you have in your pamphlet. One is that I am speaking today instead of tomorrow, and one is that I've changed the title of my talk. So I'll just note that the title that's in the schedule was this K-nearest neighbor thing. That's a sort of new project I've been working on with some people looking at some summary statistics for measuring large-scale structure beyond two-point correlation functions. When I submitted my abstract, I was a little bit overly optimistic about how much progress I would make on it this summer. So I've shifted my talk to talk more about work I've been doing within DES with many great collaborators, including some here. All right. So if I'm going to talk about how we can use galaxy surveys like DES to test our understanding of the behavior of gravity on cosmological scales. And so I think to do that, I think it's worth talking a little bit about, make some framing thoughts about how we approach cosmological tests of general relativity. And for that, I want to emphasize that general relativity as a description of gravity is one component of our standard cosmological model, which we generally refer to as lambda CDM. The other ingredients include this description of the composition of the universe being made up of dark energy and dark matter, cold dark matter, cosmological constant dark energy being part of lambda CDM. This often implies flat geometry and some specific properties of initial perturbations from, for example, a theory of inflation. So the goal of, I would say, most of cosmology experimental efforts is to use observations of the large-scale universe to constrain this model. And that's generally done in sort of two broad ways, well, many ways, but I'm going to split them into two broad ways. One is you can look at how these ingredients, what implications they make about the expansion history of the universe, as well as the evolution of fluctuations in density and structure within that background. And so by analyzing observables associated with these two things, we can compare our measurements to the predictions of our model and look for gaps where this simplest lambda CDM model doesn't quite match observations, and hopefully that'll give us some clues to develop a more fundamental understanding of most of the pieces of this model, so dark energy, dark matter, et cetera. When we think about ways that we might want to test whether general relativity needs to be extended on cosmological scales, the motivations for looking at that are tied, can be tied to our desire to understand what dark energy is, what is causing cosmic acceleration. So, you know, as I'm sure we're all familiar, Einstein's equation describes the relationship between the curvature of space-time and the matter and energy in it. And there's some freedom to, you know, move stuff from one side of this equation to the other and redefine fields. So there's some ambiguity in defining what counts as a dark energy, what counts as modified gravity. There are people who have much more expertise in this than me that might make different distinctions. But, you know, one of the things you can ask when we're trying to understand dark energy is whether the accelerating expansion of the universe could be a sign that general relativity needs to be extended in some way. More conservatively, you can also ask, by looking at models which extend general relativity and constraining them, we can look at where general relativity and what properties of gravity have been really well tested and constrained. So what deviations are still allowed given observations. And if we're looking at ways to extend our description of gravity, there are many possible ways to do this. So this is a slide by Tessa Baker that is fairly busy, but just kind of is meant to show that there's a lot of approaches you can take that if you want to go beyond Einstein's equation in describing gravity. And I'm sure that mainly to just advertise that there's a big model space out there to explore. And if you have a favorite one of these models, so different people will make arguments for some of these models or others being more theoretically well-motivated or stable or interesting to look at for various reasons. You could go and take your favorite model and do the very hard work to go all the way from your Lagrangian or something that you could write down to your observables and get some insight of how that specific model is constrained. The thing is, there's this big model space of possible ways to change our description of gravity. There's not like one or even a couple most favored of these models. So there's a big model space, and so it's not particularly feasible to go through and check everything, or at least that would be a very sort of expensive effort in time and computing power. And so I like to think of approaches to testing general relativity and just in general our standard cosmological model, the lambda CDM picture, sort of on a continuum from sort of more theoretical approaches to parametrizing deviations from GR to more phenomenological ends. And sort of on the most phenomenological end, I would put these tests where we look for tensions between experiments. So you can constrain lambda CDM parameters using different observables. For example, this is a plot I'll show slightly bigger in a slide or two, or a few, of sigma 8 or S8 constraints on the amplitude of matter density fluctuations in the universe from the CMB and from lower redshift large-scale structure measurements. And sort of in the middle, you can array a lot of different ways that people parameterize changes to gravity. If you're generous, you could put a lot of different lambda CDM extensions sort of on the more phenomenological end. You add parameters if gravity changes and you're trying to fit a WCDM, like a dynamic dark energy model, depending on where the changes to Einstein's equation show up, that you might pick that up in your WCDM parameters, even if that's not explicitly designed for changes to gravity. If you want to be more on the theoretical end, you can try, but you don't want to have to take every specific formulation of a model and go all the way to observables. You can look for more general models. So this is where people look at EFT of dark energy models or the Horndeski gravity, very general descriptions of beyond GR models you can write down. The challenge there comes that these general models end up having a lot of degrees of freedom that are frankly so many that it's very difficult to be able to constrain all the parameters you end up with, and specifically, which is going to be kind of my focus of a lot of this talk, is to constrain them robustly and make sure that you're not confusing some astrophysical or modeling uncertainty for new physics. So for this talk and for the types of constraints that I'm going to be talking about, we're very much on the phenomenological end of things. We're introducing parameters that can look for certain physical effects that could come from changing gravity, but could come from potentially other things, and trying to get a good handle on what we can say and what we can't say with our available data. Okay. So given that context, I'm going to talk through an approach to constraining deviations from GR, these very phenomenological model extensions, with dark energy survey data. So I'm going to spend a little bit of time introducing the analysis we do with DES, combining galaxy clustering and weak lensing measurements, and then I'll talk through some of the ways that we can use those measurements to constrain gravity. Okay, so some of these slides will be familiar to people that were at Cosmo last week, but just as there were a lot of talks, so it's good to give another overview. So DES is specifically an imaging survey, or sometimes we say a photometric survey. So that means in contrast to pointing like an optical fiber at each galaxy and getting a really good redshift measurement, we're taking images of the sky with a giant digital camera on a telescope. So we that means that we can observe a lot of galaxies and we can get information about their shapes. But a downside of that is that rather than having good spectra, which would give very precise redshift measurements, we have to try and infer their redshifts by looking at how the spectra of different galaxies, so this is an example showing an elliptical galaxy at different redshifts, so the spectra with the black lines. We look at how those spectra show up in different color filters, which DES has GR, IZ, Y. And so we have to infer redshifts from that. So we generally have pretty uncertain redshift measurements. And so rather than making three-dimensional measurements, we split the galaxies into redshift bins, or tomographic bins, and make measurements based on that to get some three-dimensional information about the evolution over time in the universe. DES completed observing in 2019. There were 6 years of observations for a total of about 750 nights of observing. There have been over 700 people involved in DES, including many from Brazil. And that data taking, there's sort of two main surveys in that. So there's the wide survey, which is a 5,000 square degree footprint, so that's 1/8 of the total sky. And then there's a separate supernova survey where certain patches of the sky were revisited at a more frequent cadence to look for transients. So DES by design, I'm going to be talking about one specific analysis measuring galaxy clustering and weak lensing, but it's designed to be a multi-purpose project. So there's a lot of different kinds of science that one can do with this data set. There's analysis looking at, in addition to the galaxy clustering and weak lensing, galaxy clusters, supernova. There's people studying Milky Way structure and dwarf galaxies, quasars, strong lensing, and solar system science, so a bunch of other things. So I'm focusing on galaxy clustering and weak lensing, but it's in general a really rich data set that gives people a lot of science to play with. Okay, so the status of DES, as I said, the data taking is completed, and we've been analyzing the data in chunks, and so currently the cosmology results that are out and that I'm going to be telling you about are based on the first 3 years of DES data. And so that data covers the full 5,000 square degree footprint at about half the final depth. So we revisit each direction on the sky a certain number of times to be able to average out some noise. So the year 3 data includes half of those visits. And we are ramping up the year 6 analysis to do the final analysis of this DES data now. And yeah, this is just an image of the DES footprint on the sky. It's kind of a funny shape, but the thing here is there's a big circle that's looking out of the southern pole of our galaxy. So the plane of the galaxy kind of goes around here. And then there's some rectangles added on to increase overlap with other surveys. So this rectangle at the bottom is here to overlap with the SPT, the South Pole Telescope CMB experiment, so to facilitate like cross-correlation experiments that can be done with those. All right. So the analysis I'm going to be talking to you today about is the galaxy clustering and weak lensing experiment, to just walk through a little bit about what those measurements look like with this cartoon. So we look out at the universe. What our theory modeling gives us is a way to predict the statistics of the total amount of matter, so the underlying dark matter. We don't see the dark matter, rather we see the galaxies living in overdensities. And we can probe the large-scale structure in one way by looking at how, when a sample of distant source galaxies in yellow, and their light travels through the large-scale structure, weak gravitational lensing introduces some very small distortions to their shape. It's only about a 0.1% distortion. But if we observe enough galaxies, we can look for the correlations in galaxy shapes as a function of their angular separation on the sky to get a signal that depends on the overall clustering of the dark matter causing that lensing. So we call that's the cosmic shear or weak lensing measurement. We can also look at another sample of foreground galaxies, which we call lens galaxies, and use the fact that they they appear in the overdensities causing that lensing. And so the galaxies themselves are a bias tracer of the underlying dark matter, so we can make a correlation of the positions of these lens galaxies for the galaxy clustering measurement. And that'll also be roughly proportional to the clustering of matter with an unknown bias factor. relating the distribution of galaxies to the underlying distribution of dark matter. And then given these two tracers, we can look at the cross-correlation between the two, so the positions of the foreground lens galaxies and the shape distortions of the background source galaxies. And so here we end up with 3 different kinds of 2-point correlation functions. And so the jargon that we use to refer to this combined analysis is the 3-cross 2-point analysis, because there are 3 different 2-point functions, 2-point angular correlations. All right. And it's a benefit of using these things together is that they have different kinds of uncertainties and different dependence on astrophysical uncertainties like galaxy bias parameters, for example. Okay, so this is what the measurements look like for the cosmic shear 2-point function. There are a lot of subplots here, and the thing is here, as I mentioned, we divide the galaxies into different redshift bins. So each of these subplots are different correlations between the galaxy shapes in the different bins along the line of sight. There are sort of 2 sets of triangle plots here, the upper and lower. That's because cosmic shear, the weak lensing, the shape distortion is a vector quantity on the sky, so it's a 2-dimensional quantity, which means you can decompose it into 2 degrees of freedom. So these 2 measurements are that signal in a decomposition of the shear. The data points are the measurements from our DES Year 3 analysis. And the solid lines are the best fit model predictions for these 2-point functions. So it's by doing the comparison of the model prediction to the data points that allows us to constrain parameters of our theory. So we can look at how changing different cosmological parameters affects the agreement between the measurement and model. And that's where we get physics information. The one last thing I want to highlight here is that in all of these subplots, there's some gray shaded regions. Those are scale cuts, so that denotes regions where we do measure data points, but we don't actually use them in our parameter inference. And that's because those are, so they're all at small angular scales here. So at the smaller angular scales are modeling uncertainties related to nonlinear galaxy bias, as well as the impact of baryonic physics, so AGN, supernova, et cetera, on the clustering of matter. So we don't trust our model enough to be sure that our assumptions there wouldn't bias our cosmology results. So we just leave those points out of our analysis. All right, so that's the cosmic shear measurements. Here are the other 2-point measurements that we use. So for our weak lensing sources, we have 4 redshift bins. For the lenses, which is a specific sample called the Maglim galaxy sample, we measured it for 6 bins, but we ended up only using the 4 lowest redshift bins in our analysis because we found some evidence that these highest redshift bins seem to be contaminated by some observational systematics related to the photometry, we think. So we're working on understanding that a bit better. Again, to go from the measurements to parameter constraints, we do a Bayesian analysis that's built on comparisons of the measurements to a model. So here, D for data is the collection of all those data points I showed you on the last couple slides. M is the model predictions for that. We compare them using a Gaussian covariance, which is shown in the upper part of the triangle here. So it's analytically computed. What this plot shows is basically each pixel row corresponds to one of those 460-ish data points that I showed you on the last couple slides. And the color marks how much you expect from those data points to covary with each other, just given different realizations of the large-scale structure. We fit this with in our lambda CDM analysis, we fit this with a 31-parameter model that includes 6 cosmology parameters, including neutrino mass, which is a choice that differs a little bit from DES from a number of other cosmology analyses where sometimes you tend to fix neutrino mass. And then we have 25 additional parameters that encompass some astrophysical and modeling uncertainties and measurement uncertainties. So we marginalize over those nuisance parameters to make sure we're not biasing our cosmology results. Okay, so that's the setup. That's sort of the general overview of what we're doing when we do this galaxy clustering and weak lensing analysis. Now, let's use that to test our understanding of gravity. So
as I mentioned early on, one way that we can test our standard cosmological model, that's sort of the first step towards doing this, is to look for tensions and ask whether the constraints we're getting from DES measurements of large-scale structure at redshifts less than about 1, do those constraints agree with what you'd expect given measurements from the cosmic microwave background and extrapolated forward with lambda CDM. And so this both plots here are showing S8, which is a measure of the amplitude of density fluctuations at redshift 0. And this is highlighting the sort of much talked about S8 tension, where when you constrain S8 using the CMB primary anisotropy information, you get you expect a higher value of S8 than what we seem to observe with a number of different weak lensing and galaxy clustering measurements. So the one that comes out of the DES year 3 analysis from lambda CDM are in these bottom 2 green points. And for our measurement alone, statistically speaking, when you look at different measurements of assessing tensions between these green points and this yellow one, we don't find a super statistically significant tension. Just looking at the S8 parameter, we're only about 1.5 sigma off. When we look at the full parameter space using some Bayesian statistical metrics, it gets a bit lower. But one could still argue that it is still intriguing that this collection of all these different measurements tend to be low. So it's quite an involved process to combine these different measurements, and there are teams working on doing that. But if you kind of maybe somewhat irresponsibly chi by eye, you might have a stronger significance if you were to combine all of these low redshift data. So not definitive, but definitely intriguing. And given how well lambda CDM performs in a lot of different contexts, we want to make sure we understand this well. And so I'm going to take this occasion to illustrate how do we think about this with a cartoon that we made for some outreach stuff online with DES. So we're trying to learn about fundamental physics by comparing measurements from different observables in the universe. If we find a tension between these observables, we have a couple next steps. And the first 2 are maybe somewhat obvious. We want to work towards making even more precise measurements. So if we can tighten our constraints, the 1.5 sigma offset, if the center of that parameter constraint stays and the error bars tighten, it can get more significant and help convince you whether or not that's real or a statistical fluctuation. As I said, we're working towards our final DES analysis, and also these kind of analysis from DES and other current surveys can also be seen as like a test bed for developing techniques and methodology that we'll need for next generation surveys like Euclid or LSST, which will be able to get us to an even greater precision. We also really want to make sure that we understand different modeling uncertainties, and so this is a place where work between different collaborations, so for example, between DES and KIDS, which is another current weak lensing survey, become really important. And just a lot of validation and just making sure you understand how your constraints respond to different contaminations and things that you might expect to affect your data. And then additionally, which is where the rest of the talk will come in, is you can explore what kinds of physics, if this tension is real, could explain that offset. And so you can ask what kind of physics could generate this sigma 8 offset. And then you can additionally ask, are there kinds of new physics that would give us a signal that we can find that maybe just looking at these tensions isn't that sensitive to? And so that kind of framing is the goal of our project, which results just came out about a month ago. So within DES, we've had an analysis team working to extend the galaxy clustering and weak lensing analysis to a number of models beyond lambda CDM. And so this is showcasing some of the people that have been involved in that analysis. The models that we constrain include time-dependent dark energy of state. We looked at non-zero spatial curvature. The ones that I'm going to highlight in the remainder of the talk are a modified gravity parameterization and then a phenomenological test where we constrain sigma 8 in different redshift bins. And we also studied sterile neutrinos, which I won't talk about now, but I find pretty exciting as well. So that's another thing that I'm happy to be asked about during coffee breaks. Yeah, so I co-led this team with Agnès Ferté, who just moved from JPL to Slack. And as I said, we released our results into the archive just last month. The very short summary of the paper is we tested all these models. We didn't find any significant deviations from lambda CDM, but we did a lot of work on the methodology and validation to back that up, and there are a couple of things to highlight associated with that. And yeah, we have public data online, so the data vectors, the covariants, they're all on the DES data release website. We've also shared most of the MCMC chains that we use to run this, so they're available to play with if that's something people are interested in. Okay, so as I said, I'm going to mostly focus on the modified gravity sort of adjacent models we looked at, but this is just to highlight one of the results from our analysis that is from time-dependent dark energy. And so this is when you allow the dark energy equation of state not only to be different from -1, but to have some time dependence. And you can constrain these two parameters, W0 and WA. And we looked at that. So these two plots are from the same constraint, just the right one is zoomed in a bit and showing different combinations of the data. And the thing I was going to highlight here is that the green dashed line here is from measurements from EBOS, BAO, and RSD plus Pantheon supernova. And the BAO and supernova measurements are geometric measurements basically designed, and they're powerful because they really probe the expansion history of the universe very well. And so for models like dark energy equation of state, if you're looking at combined constraints, including the BAO and supernova data, a lot of the constraining power is coming from those geometric measurements. So adding DES to those, which is shown in the purple, or adding Planck to those, which is shown in the pink, or adding everything together is in black, you can move the results around a lot, but you're already just from the BAO supernova getting most of the constraining power there. So looking at this with DES and other galaxy surveys is important because it allows you to check the redundancy of your measurement, check the consistency. But the place where DES and other lensing surveys like it can really add a lot of information is when, rather than changing just the background expansion history, you're changing the evolution of structure growth. And so I was saying, looking for tensions is approach 1 to testing gravity with experiments like DES. Approach 2 is picking a specific parameterization and constraining it. So the way we do that in this paper is using this sigma mu parameterization. So this is already on that sort of flow chart I showed at the beginning of the talk. This is a specific parameterization of modified gravity, but I will emphasize that it is very phenomenological. It's not tied to some underlying Lagrangian changing Einstein's equation. What it does is you introduce a couple generic functions which modify your Poisson equation. So mu changes the Newtonian potential, so the gravitational potential experienced by massive particles, while sigma changes the gravitational potential seen by massless particles, so it changes the lensing potential. There's different ways of defining these parameters. So if you've seen people talk about the gravitational slip, that you can use that instead of sigma or mu, but this is the way of formulating changes to the Poisson equation that we're most sensitive to, so this is what we use. So these could be generic functions. They could have some dependence on both time and scale, length scale. For our analysis, or at least for this initial analysis, we make specific choices there. So we assume that both of these functions are scale independent, so there's no k dependence. And we assume a specific redshift dependence. So we assume that they sort of turn on at the time of the accelerating expansion in the universe. This is a somewhat arbitrary choice chosen because we're interested in accelerating expansion. There's a lot of different approaches to do this. There's also ways of doing similar changes to your modeling that are more motivated by specific models of modified gravity, for example, F of R gravity. And there is work within DES led by Agnès and some other people who did a lot of the modified gravity modeling developments to extend this analysis to look at more modified gravity constraints. So that's something to keep an eye out for going into this fall. But yeah, within this initial release of Beyond Lambda CDM results, we constrain this particular parameterization. And you can see that DES in blue here is sensitive really to a product of sigma naught and S8. So we can't, on our own, distinguish between how clumpy matter is and how much the clumps of matter are driving the strength of the lensing. And so here you can see that it becomes really important as we add this modeling freedom that combining with other probes of structure growth, so here the constraint on S8 in the green contour is coming mainly from the redshift space distortion measurements that are from the EBOS collaboration. And the fact that the redshift space distortion measurements that aren't sensitive at all to sigma naught, but they are sensitive to S8 and mu naught, allows us to break degeneracies and really pin these down. There's some funny behavior from the Planck contours. The fact that these red contours are a little bit offset in sigma is related to the lensing amplitude tension, which Valerio mentioned in his talk, that the temperature and polarization power spectrum Planck have a little more lensing smoothing than you'd expect given the other constraints on cosmological parameters. But we find when we combine everything together in black, our constraints on sigma naught and mu naught shift right on top of 0 and 0, which is the values associated with general relativity. So here, maybe other than something funny going on with the CMB, we're not seeing a preference for any deviations from general relativity. So along with this model, I'm going to talk a little bit about some of the challenges that come with this. One is to note that this kind of parameterization is really only defined for when you're describing linear density fluctuations. So while you can try to use it for nonlinear fluctuations, exactly what these functions are doing, you have to make some fairly arbitrary choices. That's kind of in the prior experimenter's preference. For our approach, because they're really only defined well for linear fluctuations, we opted to make even more conservative scale cuts than from the lambda CDM analysis. So rather than just cutting out scales where we're worried about baryonic physics, we also cut basically any scales where nonlinear corrections to the matter power spectrum matter. So we lose a lot of data points, and at this point, this is really a limiting factor to the constraining power with this blue contour. Yes?
Just a quick question. How many resistance parameters do you have in this analysis?
25.
The same 25?
Yeah, so it's the same as the lambda CDM analysis, just with these two extra parameters. Or there's 22. We changed to a simpler intrinsic alignment model. So we make some simplifying assumptions on a couple of the cases. So the fact that we cut to linear only scales, one of the signs that this is one of our limiting factors is that when we compare our DES year 3 constraints from this 3x2 point measurement alone to the year 1 constraints, they're really comparable. We're not gaining constraining power, and it's because we're having to throw away so much of our data vector. So that's one of the big motivations behind this sort of looking closer at different modified gravity parameterizations and pushing that would let us push to smaller scales and keep more of our signal to noise. And that is something that, as data get more precise, that'll only help us make new physics inferences if we can actually take advantage of that precision in our analysis. All right, so I just want to spend a couple minutes talking about baryon feedback as an example of something that we need to worry about. So say we come up with a modified gravity parameterization that we don't have to cut to linear only scales. Then we're back to the scale cuts we defined for lambda CDM, which are one of the main motivations is avoiding baryon feedback. So this is a challenge even in lambda CDM. So the presence of baryonic processes, AGN, et cetera, can impact how matter clusters on small scales. And we can get a handle of the size and what that kind of effect looks like by looking at studies done on hydrodynamic simulations. And so what this plot here is the lines show the ratio between the hydro simulation power spectrum accounting for baryon effects over the dark matter only ones for a number of different hydrodynamic simulations. So you can see that there's some similarity in different shapes, but there's a lot of variations in how much of a change to the power spectrum you expect from these baryonic effects. And that has to do with different ways that these simulations implement the feedback and impacts, which is definitely out of my expertise. But the the thing to note is that there's a lot of variation in how big you expect this effect to be. So there's a lot of modeling uncertainty there. So there are ways that you could parameterize and try and marginalize over these effects, and people have done some really interesting studies doing that. For example, some DES papers on this are by Huang et al. And Angela Chen had a paper out earlier this year trying to constrain this. There's work being done cross-correlating galaxy clustering and weak lensing with like TSZ and KSZ signals to get a handle on where the gas actually is in the universe. But that's all in a state of development. In year 3 for DES, we determined that sort of the uncertainty introduced in trying to marginalize over these effects and the assumptions you have to make to decide how much of this range you want to marginalize over, et cetera, it was about equivalent to just trying to cutting the scales where you had to worry about this, so we opted to make the scale cuts. And once we made those scale cuts, we could check that our cosmology constraints, for example, on omega matter, and I cut off the label, but this is S8. We could check using analysis of synthetic data vectors, which basically you treat a model prediction for your data as if it is data and analyze it, and you can add effects from the baryons to that and make sure that you have simulated data with baryonic effects, you're analyzing it with a model with no baryonic effects, and you can see how much does that shift your cosmology constraints. And we made sure for these parameters that are sort of the main results of our analysis that the shifts between analyzing a synthetic data vector with no baryons and with baryons shifts our parameters by less than 0.3 sigma. So it's not going to bias our cosmology significantly. And just to highlight, especially because I think some of you know Otavio Alves, our ability to do this quickly for a lot of different kinds of systematics, so baryons being one example of them, we have an important sampling-based method that allows us to do this quickly that Otavio and Noah Weaver-Dick developed. Okay, so this is a challenge even for lambda CDM analyses. And then when you start looking at going beyond lambda CDM, particularly for modified gravity, it becomes even more of a challenge. So presumably, if you change the behavior of gravity, and a lot of these modifications of gravity that people consider that haven't already been ruled out, pick up some environment-dependent effects, so where in dense regions the extensions to the general relativity get screened out and they show up in underdense regions. There's a lot of nonlinear stuff that can happen here which could like plausibly affect baryonic processes and how it feeds back onto matter clustering. So I know there are research groups that are starting to do hydrodynamic simulations with modified gravity in specific models. But given things we have on hand, we don't really have a way of robustly telling how much these sort of arrays of possibilities might change in a given sort of framework for modified gravity. So ideally, if we had one like very well-motivated modified gravity model, it would really be worth it to run your hydro simulations, and in the same way that we're working to being able to marginalize over baryonic effects for lambda CDM, to be able to include that as a nuisance parameter or nuisance parameters in your modified gravity constraints. But at least at present, we don't really have tools to do that yet. And so in practice, for our year 3 analysis, and I think what's probably going to need to be the case, at least in the near future for a lot of analyses like this, the thing we can fairly robustly say is we can make sure that if the data is lambda CDM with the systematic that we're not modeling, so here baryon's an example, then we won't get a false detection of modified gravity when it's not there. If we find the detection of modified gravity, there's still some theoretical uncertainty in terms of disentangling these effects. But this is just saying, this is what we in practice do for our analysis for modified gravity and other extensions to lambda CDM. And this is a somewhat busy plot, but just showing the kind of thing we do to check for this. What this is showing are marginalized constraints on our sigma and mu parameters. Baseline means we're analyzing a synthetic data vector that it's produced with the same model we're using for parameter fitting. And then these alt data lines is where we alter the simulated data vector by adding baryonic effects or some other uncertainties and see how much compared to baseline do our constraints shift around when we do these simulated likelihood analyses. And here, this is showing that, like, basically you compare the different rows to the top row and see that we don't shift by more than like 1/3 of a sigma in any of these cases. So, and yeah, as I said, I'm giving baryons an example here, but when there are a number of our systematics that are mostly well studied in general relativity, and when we start introducing changes to growth rate or the behavior of gravity, you might need to worry about how that might affect intrinsic alignments between galaxies from like tidal effects, for example. And so that'll be a challenge here and for other analyses. Yes?
Can you give me an example of what type of modified gravity is being accounted for? I mean, this is supposedly a very low density regime. I mean, expecting something to be affected by the gravity. So what's the physical mechanism? Like, if I imagine something's going to happen there, it would do a heck of a lot in the neutron star. Whereas it also then involve a Einstein mechanism to shield all that away?
That is a good question. I think, which I am not going to be able to give a good answer. So I would just emphasize this is a very phenomenological model, just saying on the scales that we're sensitive to, how much can we constrain deviations from the Poisson equation? If we find something, or if there's a particular model being studied for impacts on neutron sources, it would be interesting to look into mapping between these two regimes. I'm not deeply familiar with efforts that have been done to do that. But yeah, there's a bit of a lamppost effect here, admittedly. We're like looking for what are deviations from GR that we can constrain well with our data, what can our data say, and the hope is that placing limits on these kind of functions or these type of parameters gives sort of benchmarks for if people are developing modeling or predictions for maybe more fundamentally motivated models to kind of compare, like, we can test for some agreement between the lensing and Newtonian potential, for example, which is, I think, the place where this kind of analysis adds information. Taking a step even more towards the sort of data-driven phenomenological end of things. So the approaches to testing gravity that I've talked about, one, tension between different data constraints on lambda CDM. Two is pick a parameterization and do your best to constrain it robustly. And approach 3 here is, I'm going to broadly say, is looking for phenomenological consistency tests. So look for ways you can maybe introduce, either split your data or introduce some free parameters to your model that test the predictions of lambda CDM, maybe without being particularly physically motivated in and of themselves. So there are approaches to doing this. For example, people look at like growth geometry split analysis, where you ask, like, do constraints on expansion history agree with constraints on structure growth? For our year 3 analysis, we do this bin sigma 8 model, where we implement it by, when we compute our linear matter power spectrum, which is one of the inputs for predicting our 2-point correlation functions, we just scale it by a constant amplitude in different redshift bins. So for each of the lens galaxy bins, so the ranges where we have the most information about the clustering of matter, we get a new amplitude parameter. We sample over that along with our 20-something nuisance parameters and other cosmology parameters. And by looking at that lets us sort of ask whether the growth rate that we're sensitive to over time, so the evolution of the clustering of matter as a function of redshift, whether that agrees with lambda CDM. So what this plot is showing is the derived constraints on sigma 8 of z as a function of redshift. The bands here are the constraints from the lambda CDM analyses. So blue is from DES alone. Black is from all of our data together. And then the points are when we add this additional freedom in the model. So we can see that, in lambda CDM, as we might have expected from the S8 tension discussion, the DES only line is a bit below the everything together line, which is a bit close, which is basically at where the Planck constraints are. And when we add the freedom, we see, at high redshifts, there's a little bit of movement away from the lambda CDM line, but nothing's really that significantly offset. But as with the sigma mu parameterization, I'm going to highlight one of the other systematic uncertainties that we have to worry about, that when we add this kind of sort of arbitrary degrees of freedom to our model, and particularly when we add that many different parameters, we start having to worry about our robustness to how we handle uncertainties in our redshift measurements. So I mentioned that as a photometric survey, we estimate our distances to the galaxies based on how bright they are in 5 different color bands. There's quite a complex process that we get redshift estimates out of that. That's a valiant effort that is like a lot of the work behind getting these results to be what they are. That was driven by a number of my very excellent colleagues. But basically what we end up with is these distributions for each redshift bin of galaxies. We have an estimate for how they're distributed in redshift. And while each individual galaxy redshift isn't measured well, we can do a pretty good job at calibrating sort of the shape and width of these redshift distributions. They're not completely certain, so in our fiducial analysis, we marginalize over some uncertainties. So I'm going to be talking specifically here about the source galaxies, so the ones that we're measuring the shapes, the weak lensing from. And you can this is just a little lensing optics diagram here. You can imagine if you move your source further away or closer to your observer, the amount and the impact of lensing given some mass of a lens will change. And so there's some uncertain, so if you don't know well the distance to your source galaxy, that'll change a bit what you infer about the amount of clustering of matter doing the lensing. So that's just to try and say that estimating these redshifts is important for estimating S8 and cosmology parameters. So in our fiducial analysis, we account for uncertainties by, for each redshift bin, we have one parameter that basically lets this N of Z function shift right and left. And we marginalize over those parameters. Another approach that you could take is maybe a bit more principled, where you can do a statistical analysis of all the color measurements and what's certain about these N of Z distributions, and rather just having one shape that shifts back and forth, you can produce an ensemble of realizations of the set of all of your N of Z functions that might be feasible given your measurements. And those can be challenged, and you could, instead of sampling over these nuisance parameters that shift the distribution back and forth, you could sample over that ensemble of possible N of Z realizations. And in principle, these two approaches should give us the same constraints, or part of the validation for the year 3 analysis was making sure that we could use the simpler just mean shift parameters. And we check that by showing that whether we use we call the hyperrank, this many realizations approach, or we use the simpler and faster mean shift approach, it didn't change the S8 constraints from our cosmic shear. It does shift them a little bit for 3x2 by about half a sigma, so that's something that I think for year 6 we're going to be taking a closer look at. But the shifts are fairly small in lambda CDM, particularly for the weak lensing measurements. All right, but then we look at this bin S8 model where we're adding 3 or 4 degrees of freedom that instead of having a smooth growth function over redshift, you have these possible like step functions. You add a lot of degrees of freedom. And the constraints become less robust to how we handle these redshift uncertainties. And I am keeping an eye on the time. So I'll just to say, the bottom line here is that it turns out our DES-only constraints from this bin sigma 8 model are more sensitive than we would like to these redshift uncertainty accounting. So these two approaches don't give the same answer. But it becomes more, well, robust in at least everything except the lowest redshift bin when we combine with external data, which helps break degeneracies between the geometry of the expansion of the universe and the clustering of matter. So the sort of more general lesson here, I would say, is when you extend your model, especially when you add a lot of degrees of freedom, sort of more general deviations from lambda CDM, you need to be careful about assumptions that go into how you account for like redshift uncertainties, among other things. And then in general, as you add more degrees of freedom, combining redundant data sets becomes even more important or more helpful to your cosmology constraints. And this is my last slide before the conclusion. Just to highlight that one thing that comes in and that we looked at in our analysis, so because DES, we marginalize over neutrino mass as part of our fiducial analysis, it gives us the sort of one side effect with our results is that we could very easily produce a plot of how different assumptions about your cosmological model influence constraints on neutrino mass. And you can look in the lambda CDM row of this table, where the first column is everything except DES, so BAO, CMB, RSD, and the right column is everything together. In lambda CDM, DES basically adds no information to neutrino mass. And that was not surprising to us. We're just marginalized over it to make sure we include that in our theoretical uncertainties. But when you start looking at models which affect structure growth, this is where adding the additional growth information from DES can help break these degeneracies and distinguish between, for example, these modified gravity parameters and neutrino mass, or these bin sigma 8 parameters and neutrino mass. So this could apply for neutrino mass. This could apply for potentially many other things. But yeah, redundant measurements of structure growth are important because structure growth is hard to disentangle from systematic effects. And that, I think, is one of the main takeaway points. But summary is here just to say that, DES, we use galaxy clustering and weak lensing. There's a lot of approaches we can use to test general relativity as part of our lambda CDM cosmological model. And that when we start looking at extended models, we have to really take a close look at how we handle systematic uncertainties related to both measurements like our redshift distributions or astrophysics like Baryon feedback. And the modeling uncertainties and the scale cuts we need to do to account for that is one of the limiting factors to our constraining power already. So, there's a lot of exciting prospects for future analyses, both from DES and other experiments. We've got a lot of work to do as theorists to keep up with the increasing precisions of that measurement. So I'll end there. Thank you for listening.
Thank you, Jesse. So yeah, I got questions from this side.
So regarding the sigma 8 binning model, so in that way, when you run your MCMC, you're allowed for arbitrary steps, and nature should be continuous. So perhaps using some spline with nodes, are you thinking about that?
Yeah, I think if we update this for a future analysis, and we're looking at, we're working on constraining this with looking at DES cross CMB lensing, in particular because I'm kind of intrigued by this data point at high redshift being a little higher, and there's some other analyses using other kinds of data, which have also seen a sort of similar, like 1 sigma-ish hint of maybe there being a little more structure at high redshift. And so, yeah, we want to do future iterations of this, and I think we're going to update it instead of being steep step functions to being some smooth model. And I kind of mentioned over lunch was one of the things that comes in is when you introduce these sort of steps or effectively like shells in density, you can get, that will produce redshift space distortion effects because you're introducing sort of steep changes in your linear structure growth. The growth factor gets steps, and so the growth rate gets spikes. And that will have some implications for even our projected measurements, so we had to do some fiddling to account for that. And yeah, so smoothing the model that we used to introduce this will allow us to have that be less like delta function-y and better behaved. So I think that'll be something we're looking into.
Ricardo is also going to get some questions from that side. Any further questions? Okay. Oh, Jesse will be around for a couple of days. So yeah, so let's thank Jesse again for this nice talk. And so now, Antonino, we have time to set up a little bit. So Antonino, you have 25 plus 5, okay?
Yes. Plus 5. I thought it was 20 plus 5.
Or 20, oh, 20 plus 5? 20 plus 5.
22 plus 3.
20 plus 5. Yeah, have to connect the computer. It's coming. No. No, no. Try again, try again. Okay, so next speaker is Dr. Antonino Troja. So Antonino was a postdoc here at ICTP-SAIFR a couple of years ago. And now he's working back in Italy, in Padua. And he's working on Euclid. So he's going to talk about the Euclid mission NISP instrument, performances and data simulations. Thank you, Antonino.
Okay, thank you, Rogerio, for the nice presentation, and thank you to the organizer for giving me the opportunity to talk about Euclid, and especially the near-infrared instrument. As Rogerio told you, I'm a postdoc in Padua. I'm also the guy who is between you and the coffee break, so I will be brief, and I hope also clear. I'm talking today, I will talk on behalf of the collaboration that works with NISP. And here you can see the logos of all the institutions that has people who design, developed, test the near-infrared instrument of Euclid. This is the outline of my talk. I will give you an overview, brief overview of Euclid, the survey, the goals. Then I will talk about the instrument, the near-infrared instrument. I will show you the performances. And then I will show you the state-of-the-art of the data, of the simulation of data that allow us to already test the pipeline that will be used with the real data. So let's go to the first point of my talk. This is a brief overview of Euclid. What is Euclid? Euclid is a survey with the main objective to describe and understand the nature of the dark sector of the universe, so of the dark component of the universe, that are dark matter and dark energy, and to study the physics and dynamics of the universe. The main probes that Euclid will study are let's say the usual one, that are the weak lensing and the galaxy clustering. Especially for galaxy clustering, the two properties of baryonic acoustic oscillation and redshift space distortion will be studied into detail. The wavelength coverage of Euclid will be between 500 nanometers and 2000 nanometers. That in human language means the visible and the near-infrared interval of the spectrum of light. Here in the image, you can see the Euclid satellite assembled in France. And actually, this hand is not in the photo, okay? And as you can see, Euclid is actually assembled and ready to be sent into space. Here you can see, I'm showing you the area of space that Euclid will observe from the Lagrangian point L2. It will be, of course, is the colored one, not the black one. It will cover a portion of sky that is almost half of the entire sphere. It will observe both the northern hemisphere and the southern hemisphere of the sky. We will have two surveys. The first one is the white survey. That is the one that will observe half of the sky, up to a magnitude of 24.5. The second one is the deep survey, much smaller, just 40 degrees square. It will observe two patches of the sky of 20 degrees that will be symmetrically oriented with respect to the galaxies, to the Milky Way, one in the northern hemisphere and one in the southern hemisphere, up to a magnitude of 26.5. And all of this, it is supposed to last 6 years. The nominally time of taking data will be 6 years. Okay. Here you can see the telescope of Euclid and the connection of the telescope to the payload module. So the telescope is a Korsch telescope. This is a reflector with 3 astigmatic mirrors. The main one is a silicon carbon mirror that has a diameter of 1.2 meters. The second one is in front of the first one, and then it will reflect the light inside the instruments, where after passing through 2 high-pass filter, it will be reflected by the latest mirror. The light will be then divided by a dichroic plate and will be focalized on the near-infrared instrument. This is the one that I will talk today, and the visual imaging instrument. The focal plane has a size of 0.5 degree squared, and this telescope is designed in such a way that we avoid stray light that comes from outside the entrance of the telescope, and allow us to take images with a point spread function extremely accurate. Let's go on and let's see what's inside the payload module. So, in the first slide you saw Euclid in all its glory, let's say. Now we are looking at its intimacy, because this is the payload module. This is what's below the telescope. So the light will come from the telescope here and will be divided into NISP, that is the yellow instrument, and the visual imager. This is the visual imager that will take images, as you can see in the left panel. Will take high quality images of the galaxies in the field of view, and this will allow us to have extremely accurate data of galaxy lensing, while NISP will give us 2 kinds of data. Data photometric, the photometry of the galaxies in the field of view, and they will be take as image in the band, in the filter band that is used at the moment, and then spectroscopy, the so-called spectroscopy, the slit spectroscopy, that will give us the spectrum for each of the sources in the field of view. I will talk about this later on. The data products of Euclid, as I told you, will be of 3 kinds. We will have the images in the visual window of the light spectrum that we'll get by this, and this will allow us to get high quality data of the shapes of galaxy with high resolution of 0.1 arc seconds. With NISP, we will have two kind of data. The photometric one in the visual between 900 and 2000 nanometers that will overlap the data of this. So we will get the same data from this and from the images of the same sources from this and NISP in the photometric asset. And with these 2 data combined, we will get 1.5 billion redshift with an accuracy of 5% between the redshift of 0 and 2. Then the spectroscopic data from NISP, they will be low resolution. We will have a 0.3 arcoseconds resolution, and they will allow us to get high accuracy redshift of almost 35 millions of sources with an accuracy of 0.1% on the redshift. The redshift interval for the spectroscopic sources will be not the full range of Euclid, but an interval, a subset from 0.7 to 1.8. So this concludes my overview of Euclid, and now I will go a bit further on the NISP instrument. This is the instrument that in Padua especially in Italy, we are developing and characterizing. So NISP, what stands for? Stands for Near Infrared Spectrometer and Photometer. So as you can see, there was a lot of fantasy in choosing the name. And here you can see the focal plane of NISP that now is impossible to see because it's already assembled, and this is in the inside part of the yellow structure that you saw before. This is composed by 16 detectors in a matrix of 4 times 4. Each detector has 2040 times 2040 pixels, so 4 millions of pixels. And the kind of, the material that was used were mercurium, cadmium, tellure, the tellurium, that is the same kind of material that were used for James Webb telescope, space telescope. So this is just to give you a reference of which kind of engineering we are using. This detector will be cooled up to a temperature, down to a temperature of 120 Kelvin. And as I told you, it will have a field of view of ½ degree square. The photometric limiting range will be 24 magnitudes with a resolution of 5%, while the spectroscopy is a bit lower with 19.5 with a resolution of 0.1. So as I mentioned before, the spectroscopy will be we will use this method of the so-called slit spectroscopy. As you know, when you do spectra of a sources, you put a slit in order to get the light, to be sure to get the light only from your sources, avoiding all contaminants from the background, and also from the fact the auto contaminants that comes from the fact that the source is not a point source, but it is extended. With slit spectroscopy, you are taking the spectra of all the sources in your field of view. In this way, the pro of this methodology is that you get hundreds or thousands of spectra in one go, instead of every time point the slit to a source, take the spectra, and then moving. So this was a choice made in order to speed up the data collection. The slit spectroscopy will be performed using GRISMs. I think all of you know, but GRISMs are a particular grating that is connected to a prism that allows the light that comes inside to be diffracted in the elementary wavelengths. Again, here you can see on the right the field of view as seen by the photometric part of NISP, and on the left the same field after passing through a GRISM, and so for each of these sources we get a spectra. So what is the problem? Of course, since you have no slit, you are not able to differentiate between sources. So if you have sources that are close enough, you will get overlap of spectra. So in order to overcome this problem, NISP is equipped with different GRISM and different color that will allow us to reduce to the bare minimum the contribution of contaminants, auto-contaminants, and systematics. And this is what I show in these slides. In these slides, you see the wavelength coverage of NISP that runs from 900 to 2000. And for each, we have 3 different bands for the photometric and 4 different GRISM for the spectroscopic. The filters and the GRISM are mounted on 2 wheels that are put inside, in front of the detector. So the lights will pass from this wheel first, then to this wheel, and at the end to the detector. We have two slots that are open and open that allow you to get only one of the field of the wheel in action. So if you want to do photometry, you will get, for example, Y and then the grism open. If you want to do spectrometry, you will have the filter wheel on open and then you get one of the grisms. So the three filter will cover the wavelength coverage, and the same interval will be covered by the grisms. We have, as I told you, two different colors of the grism: red, that in the plot is actually the purple one, and blue, that in the plot is the cyan one. And these grisms are oriented in the same direction, so they will give spectra that will be oriented at the nominal 0 degree. 0 degree for us means a vertical spectrum with respect to the detector. And having two colors will allow us to work on the auto-contaminants of the sources. Then, to work with to overcome the problem of overlapping spectrum, we will have, for one color, that is the red one, three different orientations. So we could get the spectra of each sources. So pointing at the same field of view, we can get the spectrum at 0 orientation, that I told you is vertical, then 90 degrees, that it will be horizontal, and then 180 degrees, that will be again vertical, but the grism will give us the first order of the spectrum of the source. And so once you do the 180 degree, you will get that one order. For example, if it was down with respect to the source, to the 0 order, it will be up. Of course, each of these will have overlapping spectra, depending on the sources that are close to each other. But having three different kind of overlaps should allow us to decontaminate from this contribution at the most. Here in the table you see the feature of the instrument, the specifics of the instrument that I already, they are summarized, but I already talked about it in the previous slides. Okay, so let's go to the performances, because as I told you, Euclid is ready, NISP was ready, was tested, and now we know what we are dealing with. Euclid and NISP were tested in two facilities, one in Marseille, one in Liège. We did two kinds of tests. In Marseille, we characterized the instrument as itself. So we characterized the detectors, each detectors, thermal background, so the results, the effect of the dark current due to thermal electrons, but I will talk about this later, performances, etc. Then, before moving to Liège, the PLM, the payload module was assembled, and then it was put inside a thermovacuum chamber where the condition of space were simulated. So density with vacuum and temperature. Here we tested and characterized the performance of the telescope and of the assembled telescope with the payload module. So simulating an on-flight mode of the an on-flight configuration of our instrument. Now I will show you performances, the most important. Let's start from the image quality. We evaluated using characterizing the PSF. So what we did was, for each detector, we illuminated each detector with 25 point sources, artificial, with unknown spectra. And these were simulating point sources. The instruments were aligned. As you saw, there are 3 mirrors in the telescope. The second mirror was moved in order to focus the image on the focal plane of the detector. And we modeled the PSF at the pixel level with an error function coming from the Gaussian from a Gaussian Peaks integration. So the quantity that we considered was the 50% power radius of the PSF. And what did we see? This is a plot of the results of this fit for each of the modes of photometric spectroscopic modes of NISP. Here, for example, we have the red Grisma 180. Here we have photometry. And the red one, the red line shows the requirements that were, the scientific requirements that were constructed for Euclid, that were put for Euclid. As you can see, the data shows that we are always below these requirements. So the PSF is actually smaller than the one we expected, making us confident that the image level quality is actually better than the one we were supposed to work with. So this is a good news. Then we verified the spectrometer dispersion, the spectropic dispersion. Here, to do this analysis, we had to work, this was a work done in both the facilities. In Marseille, where we were testing only the NISP instrument, we take an acquisition of a spectra using the OGSC, that is an iso-optical ground equipment, is the light, let's say, if you put it simple, the light with which we light the detector. And we get the spectra as the detector should see in a safe environment, let's say. Then we put the detector in the payload module, we simulated the in-flight mode, and then we take again the same spectra with the same instrument, OGSC, and compare the two spectra. So here you can see the result from the test in Marseille, that are the reference for us, and the same results are here with the same color, where we add also the results of the Liege test, and these results are the circle, the white circles. As you can see, the overlap is almost perfect. We have a spectral attenuation, so the circles are actually smaller than the images that we take, than the spectra we take in the Marseille configuration, and we understood that this is because of the fiber that were used to enlight the detector. So it was an artificial induced problem from the input, not in the output. So again, we are happy with the results because in flight mode, NISP performs as well as is in an optimal situation. Here you can see the spectral resolution, and again, here I will be extremely brief because it's just a very easy plot with the wavelength and the resolution power that is lambda over delta lambda. And the requirement is to have a resolution power greater than 380. And as you can see, we are always above this requirement. This is 400. This is the blue Grism with errors for each wavelength that were measured. This is the red Grism at 0, the red Grism at 180. And this is the blue Grism. The point is the blue Grism in the configuration, in a second configuration. So again, we are happy with the performance, with the actual performance of the satellite. Then, and this is the last thing that I will show you in terms of performances, we characterize the response of the detectors to the dark current. Dark current nominally is the photons that the detector believes arrived, but that are actually, okay, sorry, I'm putting this in a more complicated way. In an easier way, when you have a CCD, when you are not looking at something, it doesn't mean that you don't acquire anything, because of the electronics below the CCD, there could be some electron that, because of the temperature, the auto temperature of the sensor, can just moving freely inside the detector. And this detector can be viewed as a photon. So what we did was taking a lot of acquisition with the filter wheel that avoided the light to the illumination of the focal plane in order to see the effect of these thermal electrons. And here you can see the response of the detector. Okay, look at this, it doesn't say much. What I wanted to say is that we saw some light leakage in the border that we were able to understand and remove because it was a problem from the Marseille configuration. And with this approach, we were able to find disconnected pixels, so pixels that do not talk with the computer part of the machine. And we saw that the quantity of this pixel that we want to be able to use is below 1%, with a requirement of 2% maximum. Again, the instrument works better than expected. Okay, so I go to the last part, that is the data simulation, because once we took all these, we characterized the detector, we are able to put all the real effect into a code that allow us to simulate the sky that the detector sees. So here you can see a simulation of 2400 galaxy sources. In this, of course, is a simulation used to calibrate the detector, so the sources are put in 3 columns for each detector and aligned each. And as you can, and here in this simulation, all of the effects that you saw, so the PSF, the light leakage, the spectral resolution are included. So here we are simulating, this is what actually a data collection, an acquisition would look like. Knowing, of course, the input of each sources and the spectra, we were able to test the pipeline that we applied to data, and we got this. This is a plot of the spectra. At the end, okay, these 2400 spectra sources has the same spectra in this test. So that is the blue one, the input spectra, the spectrum. So what we did was reconstruct the spectrum from the simulation, and we, as you can see, apart of the fact that the spectrum is at 28, is lower, of course, sorry, but we were able to reconstruct each line perfectly at the proper position. Here I just put the green one. Actually, there is a red one below that has a slight modification in the spectral reconstruction, but as you can see, the results are perfectly compatible. And what we want, that is the reconstruction of lines, was obtained. Okay, this ends my talk on the characterization and the performances of NISP. I just put here a brief summary of the brief summary. Euclid is assembled and ready for launch. The launch is expected to be on late 2023 from French Guinea. In 1 month, the satellite will reach the Lagrangian point L2, from where it will start to take data. And again, we expect to collect 1.5 billion galaxy shapes and photometric redshift, and 35 million spectroscopic redshifts. NISP is ready and above expectation, so stay tuned for the next phase. Thank you for your attention.
Thank you, Antonino.
So I didn't understand how exactly works this GRISM thing. So each source becomes a set of spectra. Then how do you fit some templates to?
Do you
fit some templates to reconstruct the?
This is the template. The pipeline will search for H alpha. And again, each grism will be, the results of each grism on the same field of view will be combined to get clean spectra for each sources. On this clean spectra, the pipeline that, okay, I show you only the results in the last slide, will be applied to recover the H alpha. And then for each source, you should be able to get H alpha precisely.
But okay, this is something I don't understand also. So how do you get from these lines to the spectra? From this, yes,
from this spectra. Okay. So do you think about the? No. Okay. So the point was more. The question was more technical, let's say. Than. Yeah. Okay. Sorry. So think about when you do a spectrum. You have a sources. You put a slit in front of your sources. So you take a point like source. Then this light will pass through a grating or a prism or a grism, and it will be focalized on a region that usually is a line. Okay? When you remove the slit, the slit spectroscopy is the same principle, just you remove the slit. The grism is still there. The grism is something that takes the light and focalizes the elementary component on one region. And it keeps to do the same, just that the sources are spread along the...
Right, but so this is a wavelength?
These are spectrum. These are like, for example, take this, you have the zero order here, and this is the first order, these are the wavelengths. Oh, sorry.
So if you see a line, how would you show H?
H alpha, of course, each of these line you see bidimensional, but actually as a third dimension, that is the intensity of the light. So here you will find, for example, here more intense, here less intense. That is something that you see when you reconstruct the spectrum, and you get this. This is maybe better seen here, in which you can see that each spectra is a line.
So each object is what? The one.
Yeah, each line is the spectrum of one object, of one source.
And then
okay. So you see the spectrum is a line, and here is better seen that the intensity changes along the line.
So you see the peaks, you see the spikes in the intensity.
Yes, in the amplitude of each line are, let's say, the spikes of the wavelength.
Okay.
So in the column, each line is a source, because this is something that was artificially put, of course.
Okay, thank you. More questions?
Yeah. So I think this is something I've heard in talks before. I haven't quite absorbed. Can you say a little bit, or maybe restate what you already said about the relationship between like the spectroscopic measurements and the photometric ones? Will they be looking at the same parts of the sky?
So,
will be switching from one to the other?
Okay,
how does that work?
we will switch between the one and the other. The photometric spectra will have in common the same sources of the visual imaging. So we will get with the other instrument, imaging of a field of view, and for each source of this field of view, we will get photometric redshift. And this is one part of the data set, the one that relates to the galaxy shapes. Then we go to the spectroscopic part. Here we will focus a part of the sky, a region of the sky. Then we will get a photometric acquisition. Okay. A photometric acquisition, a visual acquisition of that region, and then the spectroscopic one. But this region is, let's say, unrelated to the visual one. The visual one will the area of the sky will be the same, but the two surveys are quite independent, let's say. The photometric is one-to-one with the visual one, and the spectroscopic is a subset on its own. The thing is that both for spectroscopic and photometric, you will have visual and photometric redshift that will be used to check for the zero order, actually.
More questions? So I have a curiosity. You showed the redshift range for the spectroscopic and the photometric, and
yes.
they're different. One starts from 0.7
Yes, yes, yes.
In the beginning.
Here.
Yeah. So why the spectrometry starts from 0.7?
Because the difference between spectroscopic and photometric is the resolution, first of all. So spectroscopy is low resolution, so everything that is smaller than 0.3 arc seconds will be averaged out. And then the magnitude limit. The photometric will go up to 24. The spectroscopic will go up to 19. So everything that is deeper than 19, fainter than 19, will not be detected by the spectroscopic part. And so, sorry, when you put these things together, you find that the optimal region is 0.7 to 1.8.
Okay, thank you. Okay, so further questions for Antonino? I don't see any hands up. So let's thank Antonino again for this very nice talk. So now we have a coffee break and we reconvene at 4 p.m.
Yeah, the first speaker of the next session may Okay, so we start the afternoon session dedicated to the work of PhD students. Please, come in. Hey, yeah, we're starting. Okay. João is he's doing his PhD at Federal of Rio de Janeiro, and a talk about stochastic background of gravitational waves. Please come in, we're starting. Okay, you have 22 plus 3, say.
Okay.
Go ahead.
So good afternoon to everyone. My name is João Lobato, and I would like to thank the organizers for this opportunity to talk about a work that I have done in collaboration with Isabella Matos and professors Maurício Calvão and Yoav Vaga. So, detection of gravitational waves represents an additional and successful test to general relativity, and it's helped us to understand better massive astrophysical bodies as black holes and neutron stars, and can futurely be very handy for understanding cosmic early processes such as inflation. But beneath the detected signals by LIGO and Virgo, you have weaker signals that cannot be resolved separately by the detectors. And so we have to combine them and study them as a stochastical gravitational wave background. We expect that LISA, the first detector, space-based detector, will be able to assess part of this background, mainly the part that comes from our Milky Way, the sources in our Milky Way. And so it is a topic that will be very important in a decade or so. And our goal here is to investigate whether this stochastic background can have corrections when we study modified theories like Horndeski. Okay, so usually when we talk about stochastic background, we try to relate the detected signal to the spectral energy density of gravitational waves by a function. And the reasons we think that this can change in modified theories are two. First, the propagation equation for gravitational waves in a cosmological background changes. Is corrected by a function. And the second reason is that the energy momentum tensor for the gravitational waves also change when expressed in terms of gravitational wave amplitude. And so this can change both sides of this equation in some way. So first, when dealing with gravitational wave spacetimes, we usually separate the metric into two parts. One part varies slowly and has a high amplitude, and the other varies more rapid and is very tiny. And this tiny part is the gravitational wave, and the rest we call the background. So we will work in this framework. So there's a famous theorem proved in the 70s, if I'm not mistaken, by Lovelock, in which he demonstrates that the most general Lagrangian, depending only on the metric, that gives second-order differential equations in 4 dimensions, is the Lagrangian of Einstein-Hilbert that gives general relativity. And so the simplest way for you to generalize general relativity is to add a new degree of freedom. And the simplest way of doing that is adding a scalar field. So an example of a scalar tensor theory is the Horndeski theory, in which you have several contributions, additional contributions, that depend on functions that are functions of the scalar field and the kinetic term related with this scalar field. General relativity is retrieved when we make G2, G3, and G5 equal to 0, and G4 equals to 1. And there is another theorem that proves that in 4 dimensions, the most general scalar tensor theory, the most general scalar tensor theory that gives second-order differential equations, assuming a non-degenerate Lagrangian, is the Horndeski theory. So has this form for the action, right? And by non-degenerate Lagrangian, I mean that when you define your canonical momenta, you can solve this equation 9 for the generalized velocities of your theory. So multi-messenger observations from binary neutron stars helped us to understand that the speed of propagation of gravitational waves is very close to that of light, at least for low redshifts. And this restrains the possible Horndeski theories, which you can work on. And we call this restricted Horndeski theory reduced Horndeski. And the restriction is that the G5 function must be 0, and G4 only depends on the scalar field directly. And so the action of the Horndeski theory is just this equation 10, very much simpler than the other. We will work in this reduced Horndeski theory and try to calculate the signal detected by 2 different detectors. So before that, I need to talk about 2 simplifications we will make. The first one is that in general relativity, you have 2 degrees of freedom for the gravitational waves, the plus and cross polarization. They deform space-time transversely to the direction of propagation, gravitational waves. But in Horndeski theory, you have another mode that does the same thing, but longitudinally, so on the direction of propagation of gravitational waves. In geometrical optics approximation, this longitudinal mode does not contribute to the energy of gravitational waves and does not contribute to curvature as well. And so we will neglect this contribution, this mode here. The second point is that in the same way we split up the metric into a background metric and a high-frequency metric part, here we could do the same thing to the scalar field. So we could split it on a background part and a high-frequency part. And you can show, using the equations of motion, that the perturbation here, delta phi, obeys a wave equation, contributes to curvature, and carries energy. And so you can call this a scalar wave. But here, for simplicity, we'll neglect scalar wave as well. Regarding background evolution, we will assume we are in an isotropic homogeneous background universe. And so we will use the Robertson-Lemaitre metric. And the equations of Friedmann equations generalized in this scheme are 12 and 13. So you can see they are very complicated. In general relativity, for an arbitrary background, you have an equation of motion for the tensorial perturbations that is given by equation 14. And if you particularize for the FLRW metric, you end up with the equation 15, which is only a wave equation with friction term that has to do with the expansion of the universe. When you go to the reduced Horndeski theories, this friction term is corrected by a term that depends on the G4 function. And so this is one of the reasons we believe that stochastic background can have a correction in these modified theories. The previous equation can be solved with a wave packet-like solution, but damped by a term that has to do with this A effective. That is simply the scale factor corrected by a square root of G4. And so we can plug in this solution into the equation that gives the gravitational wave energy density, that is equation 19. And you can see that you have a G4 factor here on front that would be 1 on general relativity. And so we can combine this G4 with the correction of equation 17. Okay. And so the angular brackets here, they stand for the so-called Brill-Hartree average that filters out high-frequency contributions to the function that is being averaged. It is a space-time average with a filtering function inside. So we will make some statistical assumptions about the stochastic background to simplify the analysis. First, we will assume that it is Gaussian, and this means that you can statistically describe it fully just analyzing the mean and the variance of the signal. We will assume that it is ergodic, and this means that the space-time average can be changed to an average on the random variables. And the random variables here will be the amplitudes of these wave packets. And so we can make this changed. We will assume that the signal is statistically homogeneous. That means that the mean and the variance of the signals do not depend on the xi, the spatial coordinates. And we will assume that the signal is statistically unpolarized. And this means that there's no correlation between different polarizations. And so assuming everything, all of these things, we arrive at a two-point correlation function of the amplitudes of each polarization that have these delta functions and power spectrum in front. I would like to emphasize that here we are still assuming that the background can depend on direction of observation, this omega hat here. And this is important because the detector frame usually is not the same frame as the gravitational wave fluid. And so you may have anisotropies coming from Doppler booster effects when you go from one reference frame to the other. And so we can make the average using these assumptions. We can arrive at the spectral energy density of gravitational waves that have this form, and there are two key elements here. The first is that it behaves as a function of the scale factor with the fourth power, as we would expect, since we are speaking about radiation fluid, right? It propagates with the velocity of light. And the other thing is that it is corrected by this Q of Ti function here that has to do with the ratio between the fields in the modified theory when compared with general relativity. But this is something that depends on your choice of initial condition. And so if you want your modified theory to retrieve general relativity at some constant time hypersurface, this Q of Ti is 1, and you obtain the same expression you would in general relativity. Remembering that the scale factor will change because the equations of motion, the background equations of motion are different. And so, but the functional dependence is still the same. So even though the propagation equation changes and the energy momentum tensor of gravitational waves change, you arrive at the same spectral energy density for gravitational waves, functionally. So now I will analyze the signal. So each detector has a signal that can be split up into the strain that gravitational waves make on free particles, and a part that has to do with the noise. And what we usually do is we take two signals measured from different detectors, and we correlate them in a given window, time window, that is this capital T. And we assume that the noises are uncorrelated because we are picking up different detectors localized at different points of Earth or space. And so the signal is simply the correlation between the strains of the two detectors. And then we can substitute the wave packet solution we got previously on this expression, 24, and we arrive at this expression. And here the correction when compared to general relativity would be this G4 function inside this temporal integral. Okay, so, but the point is that the capital T here, the time window that we are detecting gravitational signal is of order of 10 years. And so compared with the background evolution, we can assume that all the background fields are approximately constant. And so this integral can be done. And we arrive at this final expression, in which we still have the function G4, but evaluated today. Okay. So this would be possible correction to the signal, but really it depends on your initial condition, the initial condition you want to give to your background universe. If you want your theory to retrieve general relativity for high redshifts, then you have to impose that the fields are the same as general relativity for this high redshift zone. And you would have to use the generalized Friedmann equations to obtain the field today. Okay, right. To obtain the fields today. And so this would give a non-trivial correction to the G4 factor there. But if you want the general relativity to be retrieved today, then this G4 factor is only 1. But then you would have, in principle, high redshift cosmology different from the one predicted by general relativity. So you have to decide which initial condition you want to give. So that's it. So concluding, assuming some statistical properties for the stochastic background, we concluded that the spectral energy density has the same expression when written in terms of the scale factor, provided that we give an initial condition coincidence to the general relativity theory. And we concluded that we can have a correction to the stochastic signal if we assume certain initial conditions for the background fields. What we could do to generalize further this result would be to assume that scalar waves are present. In this case, we are almost certain that the energy momentum tensor will have another contribution. So here you have the energy momentum tensor of gravitational waves for a Brunstick theory, that is a scalar tensor theory, a particular case of Horndeski theory, in which you arrive at a correction to the energy momentum tensor that gives corrections to the energy and furthermore the sign of stochastic background. And so we would like to investigate further how does this, what kind of corrections you would have assuming a reduced Horndeski theory. For this, we would have to take the action of the theory, expand it to second order in the amplitudes of gravitational waves, and use the averaging scheme to arrive at the general energy momentum tensor expression in terms of the tensorial and scalar parts of the theory. And that's it. Thank you.
Okay, questions for João?
Hey, thanks for the nice talk. So you mentioned you looked at what happened if you require your scalar tensor theory to match GR at certain redshifts. Mm-hmm. Do you have like certain redshifts in mind where that would be interesting or well motivated to do, like, I don't know, BBN or something like that?
Okay. I think it depends on if you're certain that your general relativity or lambda CDM, if you like, is sufficient for you to understand like CMB and inflation and everything, then I assume that you could try to choose a redshift in that scale, like I think 1,000 and yeah, like that. But not I don't have in mind a particular. It would depend on your observables and how do you think that they deviate from. How much you think that they should deviate from general relativity.
I have a quick question. I was expecting to see some prediction for the spectrum, for the slope. I mean, you're thinking about astrophysical sources, right? Binary system or stochastic?
It is not restricted to astrophysical sources. You could think of cosmological sources as well.
Ah, okay, so this
it
is
not restricted. But yeah, it is something that we are trying to work on, trying to take some particular cases of reduced Horndeski and solve the Friedman equations, I don't know, or something like that to get a numerical prediction. The thing is that this expression also depends on the spectral energy density, and usually you relate this to the luminosity of galaxies. Mm-hmm. And for you to have this luminosity as a function of redshift, for example, you have to have a model, and I'm not. We are not investigating this right now, but it is something that would be great to do.
Okay, because you might know, I mean, there might be a detection of stochastic gravitational waves in the 10⁻⁸ Earth region. I mean, it is not fully confirmed, but it's something that people are claiming to see in the data for pulsar timing arrays. So, yeah, since you're already on the topic, it might be good to compare what is possibly in the data there.
Yeah.
Okay. Oh. Last question.
Thank you for the talk. Have you tried to apply your work for another system of like binary of white dwarfs?
So here we are thinking about a stochastic background, and so we are thinking about sources that can vary. They can be binary systems like black holes and neutron stars, and they can have cosmological origin as well. So I'm not thinking about one restricted kind of source, but there are works that calculate this spectral energy density here for astrophysical sources like the binary neutron stars, and then you have to, like I was saying, model the luminosity of each galaxy. You assume that each galaxy is like an event on your space-time, and you combine all the stochastic all the signals that can come from all the galaxies from here until high redshift zone, and you will have and then you have to model the astrophysical part, the luminosity astrophysical parts of each kind of source, and this. But I haven't studied that part like with a lot of detail yet.
Okay. I think we can thank João again. So we remain in the field of gravitational waves. No, I was announcing shooting. We remain in the field of gravitational waves with José from the Federal University of Rio Grande do Norte in Natal. So he will tell us about bright standard sirens as soon as, yes.
Pointer.
But you have to move to the other desktop. It's not appearing there. You have to move to the other desktop. Maximize now. Full screen now. Okay. Time is ticking. Clock is ticking. Go ahead.
Okay. Okay, good afternoon. Today I'm talking about the cosmology using the bright standard sirens. And first of all, it's not working. Yes. First of all, what are standard sirens and what are the dark and bright standard sirens? First, this question is, the answer is, standard sirens is a source of gravitational waves in which we can make a direct measurements of the luminosity distance as the standard candle. So this is the analogy. We have now the standard sirens. The name is sirens is because they don't have a source of electromagnetic waves. But if we have a source of electromagnetic counterpart, this standard sirens is called bright. If not, they are called dark sirens. This bright sirens is commonly from the coalescence of a binary neutral star system, and the dark standard sirens come from the coalescence of black holes. Okay? So, from the general theory of relativity, we know that the gravitational waves have two degrees of freedom, radiative degrees of freedom, that we call H plus and H cross. And if you compute the signals from a coalescence of binary neutral star or binary black holes, you know that amplitude of the signal is inversely proportional to the luminosity distance. So, and this is what we want to perform cosmology. The order ingredient joined with the luminosity distance that we want to have is the redshift. Only with the gravitational waves, we don't have information about the redshift. So we need another source, another information to get this redshift. And if we have an electromagnetic counterpart from the coalescence of this source, we can use this electromagnetic counterpart to identify the host galaxy. And so the redshift of this galaxy, and compare and make a relationship between luminosity distance and redshift in order to perform all the cosmological analysis. One of them is to measure the Hubble constant. Here I'm showing the most famous source of this kind that the LIGO and Virgo could detect. There is the signal GW170817. It was coming from the coalescence of binary neutral star system, in which from the electromagnetic counterpart here, this plot here I'm showing the green part here show the sky position of the source from the detection from the LIGO Virgo. And this blue one is a region from the short gamma ray burst, the imprecision in the sky. And looking for this region, it was detected optical counterpart for which was identified the host galaxy in this redshift. This galaxy is the NEJC 4993, for which it was measured the redshift 0.0973. And with this source was performed the first measurement of the Hubble constant using gravitational waves. So as we have only one detection of this kind, we want to detect more of this kind of source in order to perform cosmology and look for how would be the constraints that we will have in cosmological parameters using gravitational waves. The later time cosmology, because we are interested in the astrophysical source for redshift up to 2, 3, 4, but this range of redshift, okay? So the detector of gravitational waves that we have currently is the LIGO, 2 LIGOs, one in Hanford, the other in Livingston, US, other one's Virgo in Italy, and the other one, Kagra, in Japan. So the output of this detector have a lot of noise inside it, and it could have a gravitational wave inside this signal. And how can we identify that this signal is present in the output of the detector? This is made using a matched filtering, in which consists of getting the signal multiplied by a template from a theory of gravity, and looking for if this template match with the possible signal inside the source. This match filter is computed as SNR, that is a signal-to-noise ratio. And if this signal-to-noise ratio was above a threshold of 80, is a convenience, so we can be sure that this signal is a gravitational waves inside the output of our detector, okay? This plot shows the sensitivity of the current gravitational waves detectors in function of the redshift in the frequency. And if a gravitational wave signal in Fourier domain is above this curve, so we have a detectable gravitational wave to be detected with these detectors. Here I'm showing the Fourier domain of one of the detectable gravitational waves, GW15 or 914, other already detections. Here, this dashed plots in the Fourier domain, okay? And with this current gravitational wave observatories, we can see how would be the possible source that this detector can be get. For example, here I'm showing this region is relating the redshift and the total mass of the source. All the source that is inside this shaded region is detectable source. So here we can see for a binary neutral star system in this mass range, we can achieve with the current gravitational wave detector, LIGO, Virgo, and Kagra, up to a redshift 0.1. For stellar binary black holes, we can go up to a redshift 1, and so on. But as the bright standard science that I want to have a electromagnetic counterpart is basically from the binary neutral star system, this range is very low for our proposal to study cosmology with this source. So we want to have more powerful detectors to detect this binary neutral star system up to a redshift much higher, okay? So this is made with the current third generation gravitational wave observatories. We will be in the next decade, the Asian telescope in Europe, here, showing here below. A cosmic explorer in USA, possible in future, LISA, that is not a third generation detector, but is a first space gravitational wave detectors. And same as before, here I'm showing the plot where we can detect this coalescence with these detectors here. You can see that from ICTP telescope and the Cosmic Explorer, we can detect binary neutral star system up to a redshift 6, and this is very good to our proposal of study cosmology, okay? So in this project, in this presentation, I'm going to show some forecasts of using bright standard CIRES to be detected with ICTP telescope and Cosmic Explorer to make constraints in cosmological parameters. So what we have done is simulate this kind of detections for a given distribution of detection with respect to the redshift here, and this curve here, this black, is a expected distribution for this kind of detectors. There is expected in some of this reference here, and this plot here, I'm showing the current inference of the uncertainty in the luminosity distance for this kind of source in function of the redshift that was already estimated from some of these reference here, okay? And as we know, the distribution of this kind of source and also the relative uncertainty of the luminosity distance function of the redshift, we can do the simulation of this kind here. You will see a plot of the Hubble kind plot relating luminosity distance with the redshift. And with this plot, with this detection here, this simulated detection, we can perform the cosmological analysis that we have done with supernova, for example. But with ICTP telescope, it was estimated that for bright standard sightings, it can detect around 100 up to 500 detection in 10 years of observations, okay? So this is the expected number of detection that we will have with ICTP telescope or with the other electromagnetic detector that we will join with the ICTP telescope. So the models that the cosmological analysis that we have done with this kind of mock data here, one of them is a Bayesian model selection, in which we are interested in comparing cosmological nested models in order to see how many detection will be necessary to infer that one cosmological model is better than another one. So what we have done here is simulating detection according to the lambda CDM and comparing this kind of data with other cosmological models, the omega-0 CDM and omega-0 omega-I CDM, and you see how many detections it will be necessary to constrain that the lambda CDM will be better than the other ones. And here I show one result compared lambda CDM with omega-0 CDM in this plot here, and the other one compared the most complicated model, the omega-0 omega-I CDM. And here I'm showing the logarithm of the bias factor in function of the total number of detections. So as we have simulated our data using the lambda CDM as a baseline models, so we want that this curve will be above this line here, okay? So by how many detections will be necessary in order to this curve will be above on the weak evidence or moderate evidence favoring the lambda CDM. In this plot, I'm showing that using the estimated uncertainty in the luminosity distance redshift for the ICTP telescope, we see that for 100 detection, the data will favor the lambda CDM with a weak evidence. But if we could reduce the error in the luminosity distance, for example, with using other detectors, for example, combining the ICTP telescope with Cosmic Explorer or other third generation gravitational wave detector, making a network of 3G detectors. So if this is possible to reduce this up to 20% of the original error, so we can see that we can get better results of the model selection. For example, here we can see that for a 300 or 400 detection, we can get moderate evidences favoring the lambda CDM model, okay? This is one of these results. And here, I'm showing one example of how much we can reduce the error in the luminosity distance using ICTP telescope, Cosmic Explorer, combining the two ones, and using adding a third detector in here. So here, we know that using the Fisher matrix approach, the error in the luminosity distance, the relative error in the luminosity distance, is proportional to the inverse of the signal-to-noise ratio. So if this is correct, so we can make this plot here. In here, I'm showing the relative uncertainty of the luminosity distance in function of the redshift. The blue curve here is the uncertainty expected for the ICTP telescope, The red one expected for the Cosmic Explorer. The green one here is compared to Einstein telescope. You see that the Cosmic Explorer will be better than combining two Einstein telescopes, but if we combine an Einstein telescope and a Cosmic Explorer, we can get this curve here, this magenta curve here. And if we add a third detector, we will get this black curve here. You see that adding more detectors, we are improving the measurements in the luminosities. And here I'm showing what will be the best place of putting a third detector in order to get better measurements in the luminosities. Using the same Fisher matrix approach, I'm combining an Einstein telescope here in Europe, a Cosmic Explorer here in USA, and I'm looking for the best place of a third detector like AT detector, okay? So I will put a detector here, estimate what will be the uncertainty luminosities for 300 detection in there. And this color here is according to the uncertainty, the relative uncertainty luminosity. So we are looking for the region of the position in this black region here, okay? Because there's the smaller uncertainty luminosity. So in this plot here, I'm showing that the best place of a third detector is here next to the US or here in the ocean, but we can put a detector in the ocean. So the best place of a third detector is here in the US, okay? Using Fisher matrix, okay? This is not the complete analysis, but using a first approximation, this is the best place to put a third detector. Another analysis, a cosmological analysis that we can make with this kind of mock data is the cosmography with standard sightings. So how will be the constraints in cosmographic parameters that we can get with the detection of bright standard sighting with the Einstein telescope? So we know that we can expand the luminosity distance in power series of the redshift, in which each coefficient is a combination of the cosmographic parameters. Here's the H0, the Q0, the acceleration parameter, J0, related to the derivative of the scale factor, and so on. But for a given cosmological model, for example, the lambda CDM model, with these parameters, H0 equal this value, and omega m equal this value, we have specific values of the other cosmographic parameters. So the other parameters will have these values here. So comparing the cosmographic parameters, the cosmographic curve of luminosity versus redshift truncate in several orders in this series. Using these corrective values expected for the lambda CDM model, we will have all of these dashed curves here, in which the dark one here is a curve related to the lambda CDM model, and the dashed one for the cosmographic expansion truncated in several orders. The blue one for the truncated order up to the first one. There is the Hubble-Lemaître law here, the blue one, and the other ones for the red one for this truncated up the second, the green for the third one, and so on. So how this, the curve will be the better one to perform cosmography up to truncated the series up to the third one, the first order, the second order, the third order. What will be the best truncation to this cosmographic expansion? And we show, computing the relative difference between the original luminosity versus redshift curve with the other cosmographic parameters, we want to see, we are looking for the cosmographic curve that less deviates from the original one. And we can see here that the cosmographic curve that less deviates from the original one is the cosmographic expansion of luminosity up the third order in truncation, okay? And this I show the relative difference in percentage. So we can go up to a redshift 0.71 with a deviation, maximum deviation of 1% using the third truncation in the luminosity cosmographic curve, okay? So we are working with this range of redshift to perform our mock data. And so perform the Bayesian parameter estimation in order to get constraints in all the cosmographic parameters. And here I'm showing the results of the relative uncertainty in all the cosmographic parameters, blue for H0, red for K0, and green for J0, okay? In function of the redshift. In function of the redshift because increasing the redshift, I mean increase the number of detection up to get one of these values here, 2000 for the dark curves, and for the less detection up to a redshift 0.7 for 125 detection total. The solid ones is the curves related when we are dealing with the relative uncertainty in the luminosity distance for that approximation that we have shown before, the approximation of the relative uncertainty of luminosity distance versus redshift for the Einstein telescope. And the dashed one is that one related when we can reduce the error up to 20% of the original one. So, and this yellow part here, the really yellowish region here, show the region when the measurements of the Hubble constant will be better than the ones with the shoes, okay? And we see that we will have better results using the Einstein telescope to measure the Hubble constant and so on. And if we make in that range of redshift the same analysis for supernova, we will have this constraints in the Hubble constant K0 and J0 using the Pantheon data. And we can see here the relative uncertainty in the cosmographic parameters in function of the total number of detections for that range of redshift between 0 and 0.71. And we see that if we achieve a total number of 750 detections, we can have a similar constraint in Hubble constant that those ones using the supernova from Pantheon catalog, okay? And if we reduce the error up to 20%, we can have better results than those ones using supernova data. And in summary, we have here, we have make these following questions in asking and get the answer for each one. The first question is, what are dark and bright standard sightings? And the second one, how can they be detected? And the third one, how they are useful to late-time cosmology, using model selection or cosmography or so on analysis that you want. And the third point is, what are the cosmological constraints to be gathered with third-generation gravitational wave observatory? All of this answer was performed here in this presentation. Thank you very much.
Just a comment, actually. So on slide 13.
13.
Yeah, so just a comment. So you wrote lensing barrier.
Lensing barrier.
Meaning that lensing is a noise.
Yeah,
exactly. And
the source of error in the luminosity.
I just want to comment that right now it is indeed a barrier, but with the future survey like LSST, Euclid, etc., you will have a lot of galaxy catalogs up to redshift 2, but we're the lensing kernel peaks. So you will, in principle, be very optimistic. You could de-lens somehow, so you could be beyond this barrier.
Oh, okay.
That will be really interesting for the future, actually.
So I also have a question about this slide. So it looks like combining Einstein telescope with Cosmic Explorer does better than having two Einstein telescopes. Could you say a little bit about like what the difference between the Einstein telescope and Cosmic Explorer are? Like why is the magenta dashed line lower than the green dashed line?
Okay, because if you see here in this plot, I'm showing this the sensitive curve for the Cosmic Explorer and the Einstein telescope, blue for the Einstein telescope, and red for the Cosmic Explorer. And you see that the Cosmic Explorer is a bit better than the Einstein telescope. And if you see here, you can see the blue region here is the region of the Einstein telescope and the green for the Cosmic Explorer. And you see that Cosmic Explorer can achieve a higher redshift than the Einstein telescope because just they are a bit better for detecting this kind of source. And this is the reason why in this plot here, I have that the Cosmic Explorer is better than using two Einstein telescopes.
Is that just due to like the design of the detector or the
I'm not sure if because the design of, maybe because they are very bigger than the ICE telescope, because the ICE telescope will have 10 kilometers of size, and the Cosmic Explorer will have 50, I'm not sure, 40.
So the peak sensitivity in the bucket for Cosmic Explorer can be slightly better, but it will be worse at very small frequencies because it won't be underground. But for neutron star, you're not worried about ultra small frequencies. You actually want to see the main span. But of course, I mean, these are projections. I mean, those sensitivity noise curve can change.
Thank you.
Yeah, hold the microphone from that side in case. Thanks.
Hi, I have a question about this plot. So you said that
This one or this one?
The one, the right.
The right one, okay.
Another detector to, it's better built in the US or in the ocean?
Yes, because we have less error in the luminosity distance.
So you're going to get a smaller error, but wouldn't that select more sources in a specific region in the sky? Like, I'm thinking if you build in Brazil, for example, you would see another region that you wouldn't in the US.
No,
the point select some more the same kind of sources, like in the same region of the sky, so you would get less sources from this region where in Brazil or in Australia would see. So wouldn't that be, I don't know, worse for the
look,
when you have
for each point, one of these 100 point here, this hexagonal point here, I'm simulating 300 detections around the sky in isotropic form, and this is not have to do with the position of the source in the sky. But if this detection is right above the two first detectors here, because when the detections is upper the two ones, we will have a much more signal-to-noise ratio. So the combination of the position of the third detector will be favored when they are joined with the 3-1 here, because we will have a much more signal-to-noise ratio when the three detectors are joined together. We have a much more signal-to-noise ratio.
Okay. And so another question: what are two Einstein telescope detectors?
Sorry?
What are two Einstein telescopes?
What are the two Einstein telescopes?
Yeah.
This is on
from the triangle?
A triangle.
Why didn't you consider 3?
Sorry?
Why haven't you considered 3 detectors?
3 detectors?
Yeah.
I'm considering one detector consists of 3 interferometers. In this case, I'm considering 2 Einstein telescopes separated, 2 in triangle shape, okay?
In the same place in the sky?
Not necessarily in the same place, because if you see
in the same place, in the same place, Einstein telescope will be built.
Near of the, for example, putting an Einstein telescope here and other next to the first one.
Okay.
But it could be in other places, but the improvement in luminosity will not so high with the position of the second one.
Okay.
The point is the number of detection, not the position of that one.
Very nice presentation. Thank you. I have a question about the model selection result.
Model selection.
Where you put in whether you compare WCDM or W0 WACDM, you seem to get the same order of magnitude base factors and not penalized for adding an extra parameter for the plot on the right. Is my understanding correct?
You see that have a small difference when comparing the two ones. A small difference, but they are present here. So you see here that the number is 400 detection here, and here is around 300. So you see this difference.
Okay.
It's small, but they are present.
Okay.
Okay.
Thanks.
Okay, let's thank José again. And we move to the next speaker. Pedro from UFES, from Vitória. Thank you. So now we leave gravitational waves. We leave gravitational waves aside. We go back to lensing.
Você que tem que segurar? Eu tenho que botar no bolso.
Pode colocar na bolsa.
Bota no caixa. Ok. Obrigado.
Já está lá? Seu toque?
Tá, sim. Hi.
Okay, whenever you're ready.
Okay, thank you. Okay, thank you. So first I would like to thank IFT for the opportunity to be here and the accommodation. And today I'll talk a little bit about what I'm working with my collaborator, Oliver Piatella. We're studying a little bit about gravitational lensing. In particular, we're studying the effect of the cosmological constant besides the already accounted for effect in angular diameter distances. I'm from UFES, PPG Cosmo, right? So I'll give an overall review of what's the status of the research on the effects of cosmological constant on gravitational lensing. I'll then explain a little bit about what model I'm using, why I'm using the metric that I'm using, and how I define the bending angle and how that's important for taking into account properly the effects of cosmological constant. I'll show how I'll test these corrections arising from the cosmological constant on gravitational lensing, and I'll give you some concluding remarks to finish the talk. So the main question that I'm trying to understand here is, do lambda affect the bending angle in gravitational lensing? Because when you observe the lensing effect, you already take into account the effect of lambda inside the angular diameter distances when you calculate the bending angle. So the lens map is something like this, right? And you already have inside here the scale factor, which when you calculate for a Robertson-Walker metric with cosmological constant, you take right into account here. However, maybe we're not modeling it right because we're not taking into account that our lens is immersed in an expanding universe with cosmological constant, and there are maybe metrics which are more proper to deal with this effect, the effect of, for instance, a point-like object or a black hole or another type of object immersed in an expanding universe. And so maybe there should be an effect there that not only comes from angular diameter distance calculated here, but also intrinsically from the bending angle. The first person to talk about this, more or less, was Is Ltb in 1986, and he claimed that lambda should not affect gravitational lensing because, well, it does not appear in the geodesic equations of no rays, right? When you write everything for even when you write the gravitational lensing and the ray equation for the metric, for the Schwarzschild-de Sitter metric, which already includes the effect of lambda inside the Schwarzschild metric, there shouldn't appear, right, an effect in the lens equation. But, however, Rindler and Dishak mentioned that there's an issue with how Is Ltb proceeded, which is that he didn't take into account that you can't define bending angles in Schwarzschild-de Sitter as you can in Robertson-Walker and in Schwarzschild, mainly because Schwarzschild-de Sitter is not asymptotically flat, right? So the direction, the asymptotic direction which you're measuring your bending angle is not well defined as it is in Robertson-Walker metrics or perturbative Robertson-Walker metrics or Schwarzschild metrics. So they say, yes, actually lambda does affect the bending angle, not only through the angular diameter distances, but you need to define the bending angle properly. And they derived a correction, which I'll soon show you. However, their analysis was not thoroughly complete, was not thoroughly studied, And some people have taken it into account because they have not properly taken into account the effects of the observer when measuring the bending angle. Because in the end, you still have to take into account the Hubble flow because we're not static observers when we're observing gravitational lens effect. We're actually moving with the Hubble flow. So the fact is we also need to take into account the Hubble flow, right? Which I'll soon show you. And also the paradigm was a little bit shift from using purely Schwarzschild metric to calculate the bending angle to a McVitie or in mailing Kerr-de Sitter metric to model it, right? And calculate the probable effects that should arise from this correction. However, the thing is, you see the correction derived by Rinderle and Schack shows that the correction should be negative. That is, you have an effect of the cosmological constant kind of debending the lensed object, the lensed image, because usually bending, usually gravity, of course, focuses the image of the lens, of the source object, and actually lambda does the opposite effect, right? However, as I was mentioning, there were some rebuttals to the first paper of Rinderle and Schack, which mentioned that they did not take properly into account the role of the observer, which is a commuving observer. So in 2016, Piatella took the most general metric, which takes into account a compact object, and also an arbitrary scale factor, which is the McVitie metric, right? And in it, you can properly define the mass, which you have to define, which is the mass that of the lensing object, and also the way that the universe is expanding, right? And this already makes it a proper way to define the role of the observer, because you can, in this metric, properly change the frame in which you're measuring the expansion of the universe, and also observing the lens effect, right? So the current status is when you take into account the Hubble flow, right, and you define the mass of the object properly, there is a subdominant correction next to leading order, right? The correction is really small. I forgot to add the dimensions here, but it's of the order of arcs, right? So this is sub-arc seconds, which the order of the correction. However, it is interesting because the correction is sensitive to different equation of states for dark energy, right? You can predict different effects, different corrections to the bending angle, which depend on the equation of state of the dark energy model you're using. However, the thing which I studied here is all these works, they were assuming, even the McVitie, in the McVitie derivation, which is the most general one, that we have a constant Hubble factor in the model that we're using. That means that mainly our universe is the Sitter, right? So it's a lens immersed in the Sitter universe. And the fact is, we already have detected lenses that are way farther than 0.7, more or less, redshift of 0.7, which is more or less the transition redshift from matter-dominated universe to lambda-dominated universe. And the thing is, we're modeling, if we want to measure, if we want to correct for the effect of the lambda of the cosmological constant on the bending angle, we have also to take into account the effect of the transition epoch from matter to lambda, right? Because this is where we're measuring our lenses. And as I was saying, so for non-constant age, right, for models that go beyond the Sitter, we should see effects that are beyond the Bernoulli-dominated lambda. And the thing is, how how can we predict these effects, right? And are they significant? Are they of the same order of the small lambda correction that we find when we take everything into account? And that's the question I'm trying to answer. Okay, so this is a really short summary of the activity metric. It has the nice features that for small mass parameters, it's more or less like a perturbed Robertson-Walker metric. For no mass parameter, it is the Robertson-Walker metric, right? And for no scale factor, it's more or less the Schwarzschild metric. Sorry, for a constant scale factor. Mu is defined as a kind of co-moving mass, right? Because it's the mass of the lens object rationed by the scale factor. So so you see it's taken into account that the universe, as it expands, it already has a different place. Where the lensing happens is changing, right? So one way to better understand what happens is defining the Misner-Hernandez mass, which takes into account the areal radius, right? The mass that's enclosed in a space-like hypersurfaces around the mass that you're trying to study. And okay, I'm going to choose this metric to model my effect. However, far from the lens object, that means far from where the lensing is happening, I'm trying to get an analytic form for the angular diameter distances in matter and lambda-dominated universes. So this is an expression which is analytic. This is not Taylor expansion, right? This is an exact function. Actually, this is just a series expansion of the hypergeometric function, which is not pretty, but it is analytic. I'm not doing any approximations here. So we can truncate it, and since it's convergent, it's perfectly analytic. I can go to an arbitrary order, and I know that the effects will stay to that order, right? So this is what I will be using as my angular diameter distance, which will, of course, appear when I'm trying to calculate the full bending angle. And okay, so this is the lens configuration, right? My angular diameter distance is given by that expression that I showed previously. I'll define characteristic scales, which will facilitate a lot when integrating the bending angle, which I'll soon define. And the main idea is that here we have a activity metric effect, right? That mu mass parameter which I was showing you will be taken into account here. So that mu will be an expansion parameter, which will soon be related to alpha, which is the first order solution to the bending equation. And otherwise, elsewhere, right? I'll take into account that this distance is given by the purely Robertson-Walker solved by the matter plus lambda content, which I showed you in the previous slide. Okay? So the thing is, you can have an approximation, since I'm assuming that my lens is more or less, this angle here, this YS is small enough so I can approximate the tangent here by the relation YS XS, right? And when I do this approximation, I can obtain expression 4, which gives the tangent to the ray, the no ray which I'm following, right? And the solution to this equation, I'll define as the bending angle, right, in my cosmology, in my model. So this should be the full expression. And the thing that's nice there is that it has an analytic solution. But I'm doing a series of approximations, well-motivated approximations, right, the tangent that I just told you. And the thing is, before I can perform the full integration, since you have this distance, this YS, really small in this relation, I'll assume that Y here in this equation is the first order solution to the lensing equation, which means it's just a straight line, right? Of course. we should find a straight line if you're integrating the tangent here and you have a first order solution. So equation 4 is the equation I'm trying to solve, and it's taking into account all the things that I'm trying to include in my bending angle model, right? So lambda, matter, and the effect of the McVitie metric. And the expansion parameter, of course, is alpha, since I'm including here the alpha to first order solution, okay? And this definition is not trivial. You can maybe talk to me a little bit about it later. But it's a definition that how can I say? It's not the same as the one in the usual lens approximation, right? But the thing is, you have to define an angle like this whenever you take into account metrics that are not purely Robertson-Walker, angular diameter distance, plus an object model after Schwarzschild. The thing is, it's not a pretty equation. What I'm doing here is I'm expanding x, right, as the angular diameter distance that I previously defined through that ugly series. However, as I said, everything is purely analytic. You could integrate, if you would like, this to the nth order. However, I chose to stop at third order, since I'm trying to understand if the corrections are of the same, have the same effect as the already small corrections arising from the first order correction arising from lambda. And this expression 5 is giving me the full lambda plus matter plus the first order plus the 0th order correction to the bending angle. So I can integrate this. It's analytic, the integral. It can be written in terms of elementary functions. It's not pretty, so I'm not going to show you, but I can, if you want me, I can send you the paper. And this graphic showing the red line, the correction including all the terms, that is the third order correction, right, the delta 3, which I'll define. And the blue line is the first order correction, right, if we had taken just 1 plus x here, okay, which is the first order correction to the usual Schwarzschild bending angle. Bending angle. And the thing is, this graphic doesn't tell us very much, but the thing, you have a small correction, right, to the correction already arising from lambda. However, in this graphic, you can see that there is the effect of the higher order corrections arising from the lambda plus matter transition age when you're integrating on the redshift. They are of the same order of the pure lambda correction, right? So there is an effect of the same order when you take into account lambda plus matter cosmology instead of purely lambda cosmology. So you have an effect, so you have a correction of the same order. That is, it is important to take into account the transition redshift and the transition age when you're integrating over the alarm site. And especially when you have more or less ZS over ZL going to 1, that is, we have how the closer we get the source to the lens, the higher this correction is. However, this is of course not what we observe usually. And even if it would be singular, the behavior here, we will never observe something like this. I mean, even if we should model something like this, for instance, inside our galaxy, it wouldn't be in the regime of strong lensing. So none of this would be valid. And the question is, okay, you found a correction that comes from the lambda plus matter phase, arriving from the line of sight integral. Can you, for reals now, check if everything that you've done is significant? Can you compare this with observations? And the thing is, that's what I'm trying to do. And what I'm doing is I'm selecting some Einstein rings systems, right, which are super idealized. I'm using visual inspection because I'm trying to get the most perfect rings that I can see, which allow me to use a Schwarzschild lens model. And the thing is, I'll try to get a mass prediction, right? A mass prediction from the system using all these full corrections. The 0th order, which is just the Schwarzschild lens mass estimate. The first order, which was obtained in Piatella's work, right? And the 3rd order, order, which is the correction for... Sorry. And the third order correction in this paper, right? And I'm still doing the minimization, but I can already see that, no, we shouldn't really take into account all of this if we want to model gravitational lenses in the strong regime. This is more or less what I'm trying to select. I already have a reduced set of 20 Einstein rings. I'm taking mainly from the Castle's Nest DSS for surveys, all right? And the remarks is that all of these systems have systematic errors, right? And the mass estimates are really complicated because you have to assume a mass profile already. There are no Einstein ring, no perfect Einstein ring systems, such as there are no perfect Schwarzschild lenses. And the order of the correction is still really, really small, okay? To beyond first order. So in conclusion, there's mainly not only a dependence on lambda, but also on the full cosmology, right? The correction is of the same order as the lambda correction. However, it is really small, right? We cannot measure it so far. And the usual weak lensing approximation, the usual bending angle expression and lens map approximation with Schwarzschild lenses is completely valid so far. So that's what I've obtained, and thank you so much for your attention.
Very good. Thank you. Questions?
So you are working on a space-time that is not asymptotically flat, right?
Yes, exactly.
So you cannot use the straight line as a standard curve from which you will measure your deviation, right? That's the problem.
Yes, because usually when you're doing naive strong lensing, the thing is you assume that since you're on Roberts-Walker, you can just say that the directions are given by the asymptotics from the angular diameter distances, right? And since Roberts-Walker is conformally flat, this is just rescaled by the scale factor. And however, when you don't have a metric that is conformally flat, you can't define the lensing angle, the direction which you're measuring your angle from in the usual way. So you have to define it.
I didn't understand, how do you deal with this problem? What is the definition that you use?
The definition that I use?
Yeah.
What I do now is that I integrate along the node geodesics of the metric here. So this is the geodesic equation, more or less, the node geodesic equation. What I'm doing, I'm integrating over it. Of course, I'm doing some approximation so that I can model my lens system better. More or less, that's what it is. However, this is not a trivial thing. That's what because I can talk to you about later, but it's not trivial to define bending angles in arbitrary geometries. You have to understand the null rays of your space-time. And this is just an approximation that allows us to obtain a bunch of analytic, really nice expressions, more or less.
Okay, thank you.
So McVitie is basically FRW with inside the Schwarzschild, right?
More or less.
So if you're far from the mass, can you recover the usual lensing formalisms, like with lensing potential?
No, not. Not really, because it becomes a perturbed Roberts-Walker metric, right? And it would be something like lensing with the Newtonian potentials, if you call them the same as the mass parameters, right? It becomes more or less Roberts-Walker with in the perturbed Roberts-Walker in Newtonian gauge, which is well understood, at least as far as gravitational lensing goes. However, it is not conformally flat. You can't make this metric conformally flat unless you take the mass parameter to be constant. No, you can't have a mass parameter because this violates this generates an unknown Weyl tensor.
So we thank Pedro again. Okay. I hope those of you who have a poster have already sent the one slide sparkler to Tiago. Because, okay, Tiago just uploaded them. So as soon as Eunice has finished, you can all come down and then one by one you will quickly show one slide poster. But before that, we have Eunice from Vitória who will tell us everything about Kerr black holes in the Sitter.
Hi, good evening. Thank you for the opportunity in ICTP. I'm going to talk about black hole shadows. It's been a great day talking about gravitational waves and the observations of black holes by gravitational waves. Now let's move to the regime of Event Horizon Telescope. In this work, I shall present my work on remarks on Kerr black hole shadows in Kerr-de Sitter spacetimes. This work I have done with Professor Humberto, Julio, and Emmanuel. They are based in PPG Cosmo. So I will give a brief introduction. I talk somehow about the Kerr-de Sitter spacetime, the Kerr-de Sitter revisited spacetime, and the celestial coordinates. I will also talk about the quantitative and the qualitative analysis of the black hole shadows that I shall discuss, and then give a conclusion. Black holes are regions where gravity is very strong. It is strong enough such that it can warp the spacetime and it can lead to the bending of light. So it is most probable that the black holes are rotating in nature and they are described by the Kerr solution. But then when we incorporate the effect of the cosmological constant, then we have the Kerr-de Sitter solution. The Kerr-de Sitter solution, it's a lambda solution. It's a constant, it has constant curvature, and then it belongs to the Klebanski-Demiansky class of solutions. And then recently, a new solution was proposed, not really discovered, proposed, and it is the Kerr-de Sitter revisited metric. So this metric, it has the cosmological constant, but the difference is that this metric is not a vacuum solution. It does not have constant curvature, and it doesn't belong to the Klebanski-Demiansky class of solutions. And then because of this, the authors named it the Kerr-de Sitter revisited solution. And so this spacetime, due to the cosmological constant, because you can imagine the Kerr black hole has just two horizons, the event horizon and the Cauchy horizon. Due to the presence of the cosmological constant, now these spacetimes have four horizons. And these are the cosmological horizon, the event horizon, the Cauchy horizon, and the dual of the cosmological horizon. For astrophysically relevant solution phenomena, another radius comes up, which is called the static radius, and this radius is going to be somehow important to our work. It's kind of the interest of this work. And so what's a black hole shadow? When we have a black hole and there's a luminous background, the light that is coming from the luminous background can be projected into the sky of an observer, and it will cause a bright ring with a dark region in the middle, which I will not explain so much, and that's the black hole shadow. And then for an observer to locate the shadow in the sky, we need to define a set of coordinates with which this observer will be able to locate the shadow in the sky, and these are the so-called celestial coordinates. So the celestial coordinates, they depend sometimes on the on the nature of the spacetime, for instance, the Kerr spacetime is asymptotically flat, and therefore far observers can be considered. And in Kerr-de Sitter spacetime, this spacetime is asymptotically flat. So a lot of care has to be taken on the observers, and observers that are always considered in the literature in this spacetime are finite distance observers, because there's nowhere we consider it to be asymptotically flat. So just use the null tetrads and obtain the celestial coordinates. And then what do we intend to do in this work? The tetrad formalism has been used. So in this work, we were trying to study something new, where we place the observers in this Kerr-de Sitter spacetime. We place our observer in the vicinity of the static radius. And then why do we consider this? So the static radius has a certain property which, according to me, I feel hasn't been so much studied, because in this static radius, we have that the gravitational attraction and the cosmic repulsion, they counterbalance each other on this radius. And then by the use of embedding diagrams, some authors have shown that the spacetime in the vicinity of the static radius in these spacetimes is analogous to asymptotically flat spacetime. So what I was doing with my supervisors is that we were trying to treat, to place observers in the vicinity of the static radius and treat this region as analogous to asymptotically flat. And we obtain celestial coordinates and see if this can lead to some astrophysically relevant black hole shadows. So that's a brief introduction and a brief review of the Kerr-de Sitter spacetime. This is the Kerr-de Sitter metric, and these are the proper, in Boyle-Lindquist coordinates, TR and TR, theta, and phi. And this metric doesn't depend on t and phi, so it has two killing vectors, which we shall see shall be related to constants of motion according to Noether's theorem. And then, because this, we have equation 3, delta r, it's a quartic polynomial. This will lead to the 4 horizons of this spacetime. And then, because we've spoken that when a black hole is, when there's a luminous background, the light that is coming from the luminous background will be projected in the sky. So the relevant geodesics we will use are the null geodesics, not the time-like geodesics, because the light is massless, the photons are massless. So considering the null geodesics, in Kerr-de Sitter spacetime, they have been analyzed, and I've given them here. Specifically, the critical curve which we study in this work, it is as a result of null geodesics at a constant radius, and these geodesics have various names in the literature, and here we shall just refer them to the spherical photon orbits. So the condition for spherical photon orbits is that the radial potential, which is equation 10, it has to be 0, and its first derivative with respect to r has to be 0. Solving this equation simultaneously, we obtain equation 13 and 14. 13 and 14 are the constants of motions related to those two killing vectors that we talked about, which I hope we remember. So these are the constants of motion that govern the motion of spherical photon orbits in this spacetime. Equation 10, this eta is important to this work. We find that these two constants of motion, they control the motion of orbits in various ways, especially when eta is 0 or greater than 0, the photons are going to behave in different ways. For instance, when eta is greater than 0, here I've put an example of an orbit, some geodesics which I obtained in my other research. This geodesic is moving about, if you consider the black hole shadow the black hole as a sphere, this geodesic is moving up and below the equatorial plane. So this happens when eta is greater than 0. But when eta is equal to 0, they will be confined on the equatorial plane. And so we can solve for this equation of eta equals 0 to obtain two radius, equation 15 and 16. This is the radius at which the orbits will be confined on the equatorial plane, and these are called the equatorial circular orbits. They can be moving together with the black hole in the same direction. They are prograde, and when they move in the different direction, they are retrograde. So equation 15 and 16, they form the lower and upper bound of the spherical photon orbits. So the spherical photon orbits can only exist from the radius at equation 15 up to the radius at equation 16. In between, beyond this region, they are not spherical. Okay, so that's a quick review of Kerr spacetime. It is the same review in Kerr-de Sitter revisited spacetime. We have the metric. It has 2 killing vectors and 4 horizons. Those are the null geodesics. And then by using the condition of spherical photon orbits, we obtain the constants of motion that govern the motion of these orbits. And then remember, equation 27 still is eta. This parameter, it's related to the constant of motion. It governs, it's related to the energy of the photons. So when it's 0, they are confined on the equatorial plane. So we solve for that equation, for that parameter when it's 0. We solve for R to obtain the lower and upper bound of the spherical photon orbits in Kerr-de Sitter revisited spacetime. And so that is a very quick review of the spacetime. Let's move to the celestial coordinates. So by considering observers in the vicinity of the static radius, remember we are treating these observers in this place to be kind of in an asymptotically flat region. So we obtain the celestial coordinates for Kerr-de Sitter and Kerr-de Sitter revisited as these equations. And then something you can ask is, okay, you just did that. How do you know that then these observers are going to observe shadows that have the right behavior, if I can say so? Okay, so remember, here we are considering the spherical photon orbits to make the critical curve, which we are going to study. So if these spherical photon orbits get projected in the sky to make this curve has to exhibit the property of the spherical photon orbits that lead to it. So we've seen about these orbits having a lower bound and upper bound. And so when they get projected in the sky, each and every of these orbits goes to a specific place. So this curve, you can think of it as a collection of various radius of the spherical photon region. Especially at point D is where the lower bound, the smallest radius, which is defined by, for instance, equation 29. This radius, when it gets casted into the sky, it lies at point D of this curve, and the maximum radius lies at point R. The other radius in between will lie in between the curve, but I will concentrate on point D and R. So let's analyze the behavior of this, for instance, the radius in equation 29 and 30, the behavior that it will exhibit should be seen on these curves. So in this figure 3 and figure 4, I was analyzing the lower bound of Kerr-de Sitter and Kerr-de Sitter revisited spacetime. So when this spacetime, remember there's the cosmological constant. So we analyze the behavior for changing A is the black hole spin. we are dealing with rotating black holes. And lambda is the cosmological constant. So as we see that as A is increasing, the radius is also decreasing. So we expect that at point D, this is where the lower bound lies. When we increase the value of A, the point D should be decreasing. It should be moving towards the left. It should be moving towards the left. Yeah, and so let's see. So for here we analyze for the Kerr-de Sitter and Kerr-de Sitter revisited space-time. We see on these curves as we are increasing the values of A, this point, it keeps moving in the direction with which we see the behavior of its corresponding orbits. And then for changing lambda, we see that this lower bound, as we increase lambda, this radius seems to be increasing. So we expect that at point D, as we increase lambda, this point at point D, the orbits, the curve should be moving towards, it should be increasing, it should be moving towards the right. Oh my God. What happened? Okay, yeah. As we increase the value of the cosmological constant, the point D should be increasing. In that way, it should be moving towards the right. And then here we found like that's the behavior. So we analyzed the behavior of this of the radius of the photon orbits, and we found that using the celestial coordinates that we obtain, the corresponding shadows were showing this behavior. So that was kind of our proof that okay, whatever you just derived is not invalid. It leads to relevant results. And then in the paper, we have compared some results with certain authors who had considered the same idea, not exactly the same, but they were considering the same idea. And then we found that the results they obtained were not revealing the behavior of the corresponding photon region. So the result was not correct, but then it doesn't affect the results of the article because that wasn't their main work. And then, so let me go to the qualitative analysis. Besides that, we also, because when you consider parametric curve, you can find the radius of curvature. So we derived the radius of curvature for this critical curve at points T, and at point R, and we derived the vertical and horizontal diameters. We modeled this result to M87 results, and we find that for this astrophysically relevant value of the cosmological constant, the values are indistinguishable. They are only distinguishable when we use a larger value of the cosmological constant, but this is not astrophysically relevant. And then on the qualitative analysis of these shadows is that we used the Event Horizon Telescope. There is results of, on the constraint of the characteristic radius of the shadows. And then so they say that according to their results, the radius of the shadow shouldn't be less than 4.31, and it shouldn't be greater than 6.08. So we used these results to constrain the angle of inclination and the spin of the black hole. The angle of inclination is for the observer. And then when you see in these two figures, you see that for small values of black hole spin and small values of theta, the regions are the regions that are not permitted exist for high black hole spin and high angle of inclination. So we found that using this result, this constraint on the radius, we constrained the spin of the black hole, and we found that the spin when it's greater than 0.812311, that's not allowed. With respect to M87 and the angle of inclination when it's greater than 30.5107 degrees. These angles of inclination do not pass the constraints of M87, and therefore we found that the angles of inclination that pass are small, and also for small values of the black hole spin. Yeah, so that's what we did. We analyzed the black hole shadows in Kerr-de Sitter and Kerr-de Sitter revisited spacetime. We considered observers in the vicinity of the static radius. By treating this vicinity as asymptotically flat, we found the celestial coordinates. We showed from our results that the celestial coordinates, despite our treatment, they satisfy the behavior of the corresponding photon region. We also analyzed quantitatively the shadows, and qualitatively we constrained the black hole spin and the angle of inclination. We find like the high angles of inclination and high values of black hole spin do not pass the test. So sometimes this disqualifies extremal Keck black holes from being observed by Event Horizon Telescope. Thank you for your attention.
Questions for Eunice?
Can you hear me?
Okay.
Yeah. About the figure 5 and 6.
Okay. Okay.
A is equals to 0.9993.
Yeah.
Is there a problem around 1? Can you reach this point?
The problem around 1 is that when I need to use 1, the extremal Keck black holes, they need a different treatment, which we were not treating in this. So in this work, we were dealing with slowly rotating Kerr-de Sitter and Kerr-de Sitter revisited. We were not moving to the regime of extremal, because at 1, it starts being an extremal.
Okay. Okay. I think it's more about the problem is the computational or no?
It's not computational. No, for instance, the celestial coordinates which we obtained, when A is 1, I need to express them in a different way, which in the code I didn't. Maybe I was lazy.
Okay.
Yeah.
Okay.
So
Thank
it
you.
was just me not expressing the coordinates.
Thank you.
Yeah.
While we wait for the last question, please, all the poster sparkler presenters, please come down. So, but we have time for 1 or 2 more questions.
Thank you, Eunice.
Out.
I don't know if it's a silly question, but suppose that you have the greatest event horizon telescope and you could measure the shadow perfectly. Could you use, for instance, this metric to constrain the value of the cosmological constant?
Yeah, I've been trying to do this in my research, and I think it's kind of impossible at the moment.
Impossible.
At the moment.
But is it because of observation, or is it because you can't actually distinguish this metric from the Kerr one? I don't know.
Well, I really think it's because it's just small.
Mm-hmm.
Yeah.
Okay, thank you.
But with a better observation in principle, in principle you could measure with a better observation.
With the
better observation.
Maybe if they, they say that maybe if they move the telescopes to the moon.
That's better.
Okay, thank you.
Okay, so we thank you, Eunice, and all the speakers of the session. Okay, João Paulo is the first. Yeah. So, and you will talk here, and I put microphone after 1 minute.
You have 1 minute? Yeah.
Okay, well.
So in my poster, I will explain a little bit results that we have obtained recently in collaboration with Professor Bruno, where we analyzed the quasi-normal modes for Kerr black hole using Paliver transcendents, which are essentially in the equation 3 and 4 are the functions of the tau 5 and tau 3, which are complex functions in a complex plane. And we also explaining how we could obtain a better result for the behavior of the modes around extremality. So I think it's finished. All right. And okay.
Yeah, 10 seconds more.
Okay, okay. It's very quickly. So we have two results when we reach the extremality. And go there, please. I will explain better.
We will. Thank you. So you don't need to close, otherwise we just thank them all together at the end.
Okay.
Daniela.
Yeah. Hello, I'm Daniela, and this work is about machine learning in cosmology. Basically, neural networks have become popular to accelerate parameter inference in cosmology. However, neural networks are approximators. They predict your target function, but only in an approximation of your target function, for example, the power spectra. So the question is how to avoid that this approximation error will bias your parameter inference. And in this paper, in this poster, we present a Bayesian solution, which is a new posterior for neural net-based inference. And we show that this method works in cosmological analysis of the matter power spectra. And we can see that we can even debias very inaccurate neural networks for cosmological inference. So I'm happy to answer more questions in the coffee break.
Thank you. We move to, we thank all together.
In my poster, we construct a regular extension of the particular type of extreme black hole in a model with a higher curvature term in the action. This solution, this singularization is supported by the higher curvature term. The regularized extremal solution we can find asymptotically flat, while they possess and the ADS2 times S2 near horizon geometry. The near horizon solution is obtained analytically, and some bulk solutions are constructed numerically. If you are interested in detail, so please come to my poster. Thank you so much.
Okay, hi, my name is Felipe. I am working, my poster is reconciling classical and quantum electromagnetic radiation through zero indoor energy photons. And I bring it here because radiation is arguably the most used tool to probe the universe. And understanding how radiation is produced is very important. In this work, we are using an electric charge that's accelerated for a finite amount of time and study the radiation field produced by it in the asymptotic future. We using a specific choice of modes. We can describe the inertial observer's perspective using quantities associated with accelerated observers. And most importantly, we find that in the case where the acceleration is infinite in amount of time, the radiation content is built completely from modes that the accelerated observers sees as zero energy. Thank you.
Hi, my name is Ronaldo, and my poster's title is Scalar Perturbations in Quasi-Normal Modes of Hairy Black Rose. In this work, we investigate the behavior of GD Hairy Black Rose under scalar perturbations. GD is old gravitational decoupling, is a way to decouple Einstein's field equations. In this work, we apply WKB approximation to derive quasi-normal frequencies and compare them to Schwarzschild solutions ones. And sorry, and the main result of this work shows that G Hairy Black Rose do have a unique signature that is encoded by alpha parameter, that is the gravitational decoupling parameter. So doubts, feel free to call me, and this is my email. Thank you, everyone.
Hello, everyone. My name is Gabriel Ribeiro, and I'm going to talk about the mapping of F over theories of gravity into GR. So modified gravity is some topic of interest because we all know about the shortcomings of GR in the high energy and low energy regimes. So but they can be mathematically cumbersome because they present some modifications on the Lagrangian of the gravity sector. And in this work, I'm going to present the way of mapping F over into GR. We first will introduce the field equations of F over in the Palatini formalism. That is, we'll consider the a priori, the metric G mu nu, and the connections to be independent. And then we'll introduce a auxiliary metric that will be related to the original metric by a deformation matrix. And then we'll establish in this context an Einstein equation, so we can establish a mapping between the meta sector of the two theories.
You have to leave some details of the poster. You don't have to tell everything now.
Right, okay.
Okay, so the last one.
Eu vou falar no português, eu ainda estou muito ruim em inglês. Meu trabalho é as investigações de bifurcações em modos quase normais, com constante cosmológica. E, neste caso, vou trabalhar com o campo escalar, considerando considerando constante cosmológica positiva. Va a tener un comportamiento muy interesante porque os va a tener unas bifurcaciones. Vamos a considerar asimetría esférica y también vamos a precisar de un eu esqueci o nome, de um pacote de matemática para fazer as contas e também as equações de Klein-Gordon. E primeiro vamos a fazer um pouco de Schwarzschild e depois de Schwarzschild ADS, que é mais isso eu vou fazer. Tá.
Okay. Sorry, there is one more. This is now is the real last. One is here. 1 minute.
Hello, good afternoon, everyone. My name is Juan Zarate, and in this work, I investigate the hydrostatic equilibrium of compact stars with the inclusion of anisotropic pressure. But in particular, I focus on power law model, where Fr is equal to R raised to 1 plus epsilon. And we examine a small deviation from general relativity for epsilon much less than 1. So I have to derive the modified of equations in Fr gravity. And I find that both the mass and the radius of a compact star with respect to the general relativistic counterpart are larger. Furthermore, I remark that the substantial change due to anisotropy occurs mainly in the high central density region. If you have questions, we can then discuss in coffee break. Thanks.
Okay, we thank them all now. And this is the end of today's session.
Professor, tudo foi gravado, está no canal do YouTube.